Without further ado, all the way from Minnesota, we have our very first virtual speaker this morning. We've had virtual but never live, but now we have live and virtual together, so I guess this is the uniqueness of the world today. But Paul Eager from Newfield. Paul Eager is a senior environmental engineer with Newfield. He has over 40 years of experience dealing with environmental issues related to mining and water resources, both in the public and private sector. His technical expertise focuses on water treatment, waste management, reclamation, and regulatory issues. And all the way from Hibbing, Minnesota, we have Paul and his talk, Biochemical Reactors of Mine Drainage Treatment.
Thanks, Kevin. Well, I was feeling bad about not being able to attend in person, and now after Kevin's discussion about everything I'm missing, I really feel bad. But I'm kind of excited to be kind of maybe the first virtual presenter at the kind of hybrid conference that we're having this year, and it's been really nice to have the option to both present and attend virtually. So I'm going to talk a little bit about biochemical reactors. And, as an engineer, we tend to often look at complex things kind of as black boxes. What we're focused on, well, what are we putting in and what comes out? And this project gave us kind of a unique opportunity to actually delve into one of these biochemical reactors to see what was going on inside it. Before I start, I want to acknowledge my co-authors, Candace Carries-Beatty from Winona State University. She's a long-term friend and colleague who was instrumental in helping me pull this presentation together and presented most of the graphics that we'll be showing. Basically, this is a summary of work that was done by two PhD students, Julie Labar and Dina Drennan. Julie was at the University of Oklahoma at the time. She's now at Centenary University. And Dina was at the Colorado School of Mines, and she's currently with CDM Smith. And then last but not least is a long-term friend and one of my favorite partners in crime, Jim Gusick. So this was some work that Jim and I started way before we were affiliated. I was affiliated with Newfields and Jim was affiliated with Lincoln Engineering. But we thought it was time, there was kind of an interesting story that we should spend a little bit of time and put it together. So hopefully you'll agree. All right, I know you've had talks about biochemical reactors in the past. Actually, I gave a presentation and talked a little bit about them last year. But not everyone is enamored as a passive treatment as I am, so it might be good to have a little refresher. So this essentially is kind of what BCRs look like. They typically are solid substrates. They're a mixture of organic material and limestone. Typically, there's a layer of water on top of them because we basically want to keep everything saturated so we can keep it anoxic. Flow is vertically through the media. And what we're trying to do with creating this anoxic reaction zone is to promote sulfate reduction, which is a microbial process. And Catherine did a nice job of talking about this yesterday. Why those of us in the passive treatment field like these is that they've really been the workhorse for a long period of time when we deal with mine drainage. They treat a wide range of pH, they increase pH and remove metals, and they're very effective. So again, just to summarize, this is a sulfate-reducing bacteria. These are the reactions. Sulfate-reducing bacteria need an anoxic environment, and then B need small-chain organics and sulfate. What they do then is they produce bicarbonate, which helps increase the pH, and sulfide, which reacts with the metals and produce metal sulfides. So that's kind of the model that we're working on. The sulfate reduction is really the workhorse of these systems. So this site, I had two cells operating in parallel, kind of a standard, typical media mix consisting of organics and limestone. They were large systems and they had a lot of media in them. So typically these cells, BCRs usually have about 3 feet of media. This had almost twice that amount. And they operated for about a 10-year period. So what happened was that these bioreactors were sitting on kind of prime real estate. And the company needed that land and said, sorry, the biochemical reactors have to go. So that was unfortunate, but it gave us an opportunity to go into a full-scale system that had been operating for 10 years and do an autopsy on it. So originally our scope was pretty limited. We were going to go to the site, take some samples, and do some total metal analysis, and kind of look at how it worked and see if, well, can we figure out some ways we might make it work better in the future. I realized that this was a fairly unique opportunity, and so reached out to some of my university friends and said, you know, we've got this opportunity. Do you have any graduate students who might be able to use some of these samples and incorporate it into their graduate work? And luckily we had two, Julie and Dina. Julie worked mainly on the metals and metal forms. Dina worked on the microbiology. So I'm sure those of you in the consultant world have never had this happen, where you start a project, you go out, you collect some samples, and then all of a sudden the client says, nah, you know, we're going to stop the project. So that's what happened here. And so, you know, samples had been collected. Some of them have been sent to the students. They worked on them. They finished their dissertation work, but there was never time to pull it all together to see, okay, can we tell a consistent story based on this data that was collected? So when COVID came around, I found myself a little extra time. And so I said, well, you know, this seems like a reasonable thing to put together. It'd be an interesting story to tell. You know, there's all this data. It shouldn't be that hard. Well, those are famous last words, because I'm sure you've never had this happen to you either, but the reality is never quite like your plan. And so this was much more challenging to pull together than I ever imagined. So let's get into the data and kind of see some of the challenges we had. So there was a lot of water quality data because there was 10 years of data of monthly samples. But when I started to get into it, there were just a lot of inconsistencies. And so I said, well, you know, I should at least bring out the quality assurance soapbox and stand on it for at least a minute or so and talk about it, how critical these checks are. And, you know, this is one of those duh moments. We all know this is important, but often it's sometimes it's easy just to push off to tomorrow, but it's never a good idea. Some of the challenges working with the data from Dina and Julie were obviously they're in different laboratories, they're using different techniques, and the samples they had came from different cells. So there's, as I said, there were challenges here. Let's look at the water quality. Okay, so this is the median values for the whole 10 years of operation. So the input is fairly typical acid mine drainage, you know, pH in 3s, high acidity, high iron, high aluminum. Trace metals were present, relatively low concentrations, and a relatively low concentration of sulfate. Okay, well, did the cells do their job? Well, yes, they basically increased pH up into the circumneutral range, greater than 6. As you can see, produced a net alkaline water, removed most of the iron and basically all of the aluminum and the trace metals, and a substantial portion of the sulfate as well. So overall, it looked like they were working quite well, but one of the key questions with these systems is, you know, how long will they work? And that's always a question with passive systems, particularly the biochemical reactors. So what I wanted to look at was essentially some of the key indicators, first one being pH. So this is pH versus time. The orange circles here are the input samples, and you see they're all basically below 4. And then the pink and the gray are the outflow. And in general, they're all above 6. And there really does not seem to be any trend downward suggesting that the system is losing capacity to treat. Because there was this one exception with this period of time where all of a sudden the pH just went crazy. The input pH dropped from 3, dropped 2 orders of magnitude down to 0.8. And all of a sudden the cells were producing acid drainage in their outflow. Well, when I went into the data, I realized that all of the lab data said that all of these outflow samples were net alkaline water. So clearly there was a problem in the pH meter and the field readings. So again, you know, cue the soapbox, do your QA checks as soon as possible. The other one we wanted to look at is sulfate removal. Again, this sulfate reduction is the engine that drives this treatment system. If we don't have sulfate reduction, the system is not working like it should. So what we see is a lot of scatter, a lot of variability in the inlet data, and obviously concentration removal, less removal when concentrations go high. But what we see in general is that there's always removal. And again, no evidence of decreased removal. So again, the system is working, and it was working when it was stopped at 10 years. Again, an important consideration for long-term estimates of how long these systems will last. So typically, in the old days, we used to say 10 to 20 years. We're now seeing systems that have run for 10 years. And so now we're saying, well, at least 15 and maybe 15 to 20, 15 to 25. So good news that the systems seem to be more robust than we initially expected. All right, so let's talk about the substrate. And this is work from Julie Labar's PhD dissertation. Okay, so this is kind of a schematic of the sampling of the site of the cell. There were 5 sites. She was able to analyze samples from 4 different depths. So what I want to point out is this photo in the lower right here. You can see that this doesn't look like that model that I showed you originally, where we had this layer of water, we had this distribution of flow on top of it, and perfect uniform flow through a heterogeneous media, which is always a little bit of a stretch in our assumptions. But what is all of this? Well, it's woody vegetation. And that's what these symbols represent here. Again, this is not something we want, particularly woody. We don't typically want vegetation on these systems. The woody vegetation in particular has much more deeply rooted than the wetland species. When they demolished this cell, they found roots down to as deep as 18 inches, most of the roots being in the top foot. But, basically oxygen is transferred down to the roots, which is not something you want if you're trying to promote an anaerobic environment. The other thing that I noticed when I was on the site and walking around is that the woody vegetation tends to produce its own microtopography, since the surface tends to mound and less water is there, which allows the woody vegetation to spread, and that's kind of what's happened. And so what we see, the other thing that we see here is that this is the inlet line, and the inlet line just stops when at a single point. Originally, this inlet went all the way across. It was a perforated pipe, but any of you who've worked with high iron water knows that iron loves to come out of solution and plug things, and that's what happened. So they basically had to cut off the inlet pipe. So now we basically have a single point coming into the system rather than a dispersal of flow. Okay, so let's kind of look at what she found. What we see too here is, so we have all kind of this to point this out, is that we have this woody vegetation. We have some lower areas that are, the vegetation was primarily cattails. Okay, so this is a surface sample, 0 to 3 inches. It's total metals. Again, this is a summary. There's a lot of data here. Again, I can't talk about all of it. Again, I had hoped to be there in person so we could sit down and talk about some of this data over a few beers, because data analysis always seems to go better when beer is involved. But these are laid out to correspond to the sampling grid. So for example, this site corresponds to the middle sample point. So what we notice first, and I want to talk primarily about iron initially here on the surface distribution, very high iron concentration near the inlet, tends to fall off as you move in this direction around the cell. That tends to correspond with the lower areas where there are cattail vegetation. The higher essentially the areas that are higher slightly in elevation have woody species, show much lower iron. So this dotted line is just a point of reference. This is 10,000 milligrams per kilogram or 1% metals. These are log scales. So again, I thought it was helpful to have that line just to kind of help you kind of orient in terms of concentration versus the location in the cell. So the next thing I want to do is then kind of look at not only the surface concentration, but concentration versus a function of depth. Again, same reference line at 10,000 milligrams per kilogram. So what we see, I'm going to focus again on iron. Iron concentrations decrease with depth at all the sites where there was, higher concentrations at the surface. Concentrations where sites where there was very little iron at the surface seem to be relatively uniform. So not much variation with iron as a function of depth. And you notice that at the lower concentrations at the deeper depths, iron, where we did see removal, approaches essentially this 1% number. So suggesting that most of the iron removal is occurring, near the surface. And that by the time you get deep in the substrate, we're not seeing much metal removal. Trace metals are a little different story, particularly zinc. And this is another one where I really would love to be sitting down with some of you to maybe kick some ideas around this. So what we see near the inlet is we see certainly lower zinc at the surface, increased zinc as we go deeper into the substrate. We see copper at the surface, again, higher concentrations deep, and then tending to decrease, which is what we see here at the site with the copper as well. So again, most of the removal of the copper seems to be, at most sites, seems to be affiliated with the surface material, but this site seems different. So our speculation is that this is near the input. We have low pH water coming in. There's a little supportive data to show that the calcium in these first 3 inches was depleted. So we think that the main removal mechanism occurring here was really limestone dissolution and neutralization. Copper can much more readily co-precipitates with iron than zinc. As we get deeper, we then start seeing more accumulation of zinc. And so I want to look at and see if we can explain that with the metal forms work that Julie did. So we'll talk about that. I put this slide in not to spend a lot of time talking about it, but for future reference, if you want to go back and see exactly what Julie did. There's a lot of different sequential extractions. I think they're interesting. I look at them as indicative, not definitive. But
10 minutes.
Okay, but it does give you some idea of where the metals are sitting. So that they just showed, but I want to focus on 2 specific sites, the one where we see a lot of removal and one where we see basically very little removal. So in general, what Julie found at all her sites was that the metals associated with the sulfide fraction were the highest percentage. And so this is the percent of total extraction, and this is sampling depth. And so this essentially is a site that does not show much removal, fairly flat concentration profiles, but still most of the metals are present in sulfides. This is a site where we see this increased removal of copper and zinc at depth. Again, what I'm focusing only on is the zinc extraction data because I don't have time to spend on all the data here. But what we see is a dramatic increase in the percent of metal zinc that is present in sulfide. Again, this is what we'd hope to see in this type of a system where we're basically trying to produce metal sulfides. So again, it's a nice correlation to basically what we're hoping to see. All right, I've only got 10 minutes. I got the 10-minute warning, so I'm gonna have to pick up the pace here and talk about microbiology. So again, I'm an engineer. I don't know a whole lot about microbiology. I admit my ignorance right up front, and Dina said, any hard questions, I can give you her contact information and she'd be happy to help you. So again, a similar sampling grid. Here, the inlet flow comes in from the northwest and terminates near the center of the cell. So again, Dina had samples from various locations in the cell and at various depths. I want to point out that the vegetation in her cell, again, it had vegetation, but primarily cattails, much less deeply rooted species, but it also then presents an issue because it tends to create some microtopography, sorry. So again, this is a fairly standard technique. Catherine talked about this much more eloquently than I did.
Oh, I ate.
I'm sorry, I'm getting some feedback on the mics here, or somebody's talking. Thank you. So, but it's a standard procedure, and you extract the DNA, you sequence it, and then you identify the groups which were there. She also did some geochemistry, a very different sequential extraction that Julie did because she basically just got 2 groups of metal forms. Later on, we're going to talk about the sulfide bound form. So again, what we need here is we need basically functional groups that break down this complex organic matter to form those small chain organics that are needed by the sulfate reducers, and we need sulfate reducers. Those functional groups are present throughout the reactor, and there was no major differences spatially with respect to diversity. There was some increased methanogens in the deeper samples, which Dina thought might be related to a decrease in sulfate in the deeper samples. This is the zinc, the sulfide-bound zinc, and this is some really interesting work that Gina did. So what I like about this, it shows not only the aerial variation, but it combines the depth variation as well. So it's a very elegant way of plotting it. It takes a very long time because when I asked Dina if she could do more plots like this, she said, no way. So, but here what we've got is milligrams per gram of different units of sulfide-bound zinc. And the blue areas are the areas with the highest concentrations. And so what we're seeing again is a concentration of zinc removal basically at one site and at depth, similar to what Julie observed. So this is the individual data. This is the averages. The color scheme changes a little bit. Blue here being light, lower concentrations, red being higher concentrations. But Dina was able to do some statistics. These are p-values and show that there was a statistically higher concentration of zinc sulfide bound metals at this site, BC2. So she said, okay, well, do I see any differences in the biological community at that location? And what she did is she did do that and found out basically that this was statistically significant, and that there was an increase in sulfate reducers where we had the highest concentration of sulfide-bound zinc. So again, this is nice data because it supports the whole operation of the biochemical reactor. So what does it all mean? The BCRs effectively treated the water. You know, they raised the pH, they removed sulfate, and removed the metals in solution. There was no evidence of loss of treatment. Obviously, a lot of variation, though, so not really fitting our model of distribution of input flow and perfect vertical flow through the entire substrate. Trace metals were removed primarily as sulfides, which is what we had hoped, and that there was a diverse microbial community established throughout the substrate. So what did we learn? Well, obviously, it was critical to manage the water level and vegetation. You know, again, the system was not designed to have vegetation, but again, often you design something, it doesn't get built or operated the way you would hope it would be. And, you know, elevated iron is always a problem. That's nothing new in this site, but it does cause problems at this site. But I think the main takeaway is that the microbiology that we need for this system to work is present throughout the reactor, and the problem is the flow distribution. All right, well, this was done about 20 years ago. And so the question is, well, what would we do differently now? So some of you might have suffered through this presentation that I gave last year, where we talked about new advances in passive treatment. And I think certainly we would look at some of these. And we basically, I talked about these last year, but the key is to remove the iron before it gets to the BCR. That reduces the input acidity, it avoids the plugging issues, it reduces the BCR size, and may allow alternatives to the BCR. Again, this information is all described in last year's presentation, which is available online. Just quickly, iron terraces. Iron wants to come out of solution. The idea behind an iron terrace is you build something that allows that to happen, and these iron build up and continue to remove iron over time. The second is an acid neutralizing cell. These utilize aerobic processes. It's a mixture of coarse wood, which provides a more permeable substrate, and then fine-grained limestone. Essentially, you're using limestone dissolution. The limestone is small enough that it dissolves before it plugs. So, and another thing that we've been working on recently that I thought was worth saying and including, and particularly since I got to use a quote from Homer Simpson. So I don't know if this is the low point of my presentation career or the high point. I guess it depends on your feelings about the Simpsons. But we've been working a lot on semi-passive bioreactors, also known as bugs on booze. What these are their carbon-fed bioreactors. Sulfate reducers need small chain organics. You can either get them by breaking down complex organics or supplying them directly. The most common thing that's been used in the past is ethanol, hence bugs on booze. Carbon is more available, so you get faster reaction and smaller footprints. They use a coarse rock matrix, higher permeability, less chance for preferential flow. And it gives you some adjustable, this is the feed tank, it gives you some ability to adjust the carbon feed to change, to adjust for changes in your input chemistry. The other thing, since these systems produce excess alkalinity, some of that alkalinity can be recirculated back to the head of the cell, where it will raise the pH and precipitate some of the iron. This is clearly not as passive as a substrate-based bioreactor, but it does require more efforts for maintenance, but it does provide some nice benefits and is something worth looking at. With that, I'm probably a little bit long, but hopefully we'll have a little bit of time for questions. So thank you.
Thank you, Paul. Yes, question? If you'd like, that'd be great. Paul, gentleman's just going to come up to the mic and ask
Okay,
you
thank
a
you.
question.
Hi, Paul. Thanks for a great talk. This is Seth D'Imperio with Environment. I have a microbiology question for you, so I hope you don't mind. Just wondering whether or not for those sulfate reducers, you have any indication of the distribution of those and which sulfate reducers you've got in there, and if that changed at all with depth.
Ah, boy, that's a really good question, Seth. And I'm going to fall back on my disclaimer that I'm not a biologist, a microbiologist. I think that data is available. I do have a table that I can share with you that shows some of the organisms that Dina found. I don't know if I can pull it up right now. That's
That's all right. And
yeah.
Perhaps if you can just maybe send me some of that contact info, I can talk with Dina about that a little bit.
That would be much preferable than me trying to stumble through and kind of trying to pretend I'm a microbiologist. So,
Great, thank you.
But the one thing I did want to add is that I know Catherine talked about this yesterday about the importance of microbes. And again, I don't understand much about them, but I know they're really important. They are kind of like the Rodney Dangerfield of passive water treatment. They don't get no respect, but they are critically important. And it's fun to be able to work with people like Dina to help to try to educate some of us about what they're doing and their importance.
Paul, we have one more question here.
Sure.
Good morning, Paul. This is Warren. Welcome back to the conference.
Hey, Warren.
The question I always have about bioreactors is, are they effective year-round, or were they subject to freezing and thawing?
So that's a very good question, and it's always an issue. This particular site did not have severe winters, so it was not an issue there. Actually, the original design did have a cover, kind of inert material cover, but again, not all systems are built as they are designed, as those of us in the consulting world unfortunately find more often than we would like. So when we have systems where we're operating in cold temperatures, then we often use kind of an inert cover. So actually then they are not exposed, they're actually insulated. When the inert cover it's often something like wood chips, for example. So you actually don't have that free water surface, you have water surface in an inert cover. So that provides the insulation. And it also depends, like one of the bugs on booze reactors that I did years ago, we actually were working with in northern Minnesota, which, as you know, is quite cold, but the water coming in was warm. And so having it below the surface of the rock matrix and the warm water basically kept that system operating all winter. So it can be done. It is a microbiological process. You often see slower reaction rates in the winter. But again, it's something that you need to take into account in your design. But winter treatment is certainly doable.
Paul, thank you, and thank you for taking the time for being our very first virtual presentation. And I'm sure the audience was very thankful for you also.
Thank you.
And now we'll move on to our next talk, Limiting Destructive Testing of Geomembrane Lining System, We have Evan Andrews, received a Bachelor's of Science degree from Clarkson University in Civil Engineering and Environmental Engineering. He is a licensed professional engineer. He is based in North Carolina and serves as a chief engineer for Sequoia Services, a heavy civil and environmental construction contractor.
All right, good morning. Thank you for having me here. It's been a great opportunity to travel out to Montana, where it's, I think North Carolina right now, wet bulb was like 106 yesterday. So all the safety topics I was, for meetings I was on was, stay inside, hydrate, and we're outside, being cold in shorts and t-shirts. So again, this is maybe taking something from the last slide, something completely different. Any Monty Python fans out there? Not a lot have been heard from, geosynthetics maybe in this conference, but where we're working out in the East Coast and mainly with in the energy industry, CCR, coal combustion residuals, a lot of work, a lot of research, and I've been, most of my career, last 20 or so years, has been working with geosynthetic systems. And background, so my co-author with this, with Wood, was not able to make it, so I'm just kind of going solo today. But so on this project, my role, I was the lead engineer for Duke Energy, which is the nation's largest energy utility, and I was the landfill manager. So I managed 22 landfills in 5 states, dealing with coal ash. And so we need to get a team together to fix a problem, and we saw an opportunity to do a pilot project to try to address something that's been vexing the industry for upwards of 40 years. And just quick to note, to your audience, just show of hands, people that have seen, designed, operated a geosynthetic lighting system. Seen them? I mean, just to see if I'm coming from Mars here. It's about half the room, so I'll try to tailor this. But so what we basically, the project and all these topics could be their own projects. I'll try to move kind of rapidly through these. But I'm going to cover what is geomembrane testing, QC, QA. What do we do? Where did it come from? How do we start doing these things? And in a bar later, we can talk about the origin of specifications and how they just never go away. When someone gets one they like, it just lives forever. But so I'll go through some, how we do this testing origins, what are we doing as far as the current practice today, and then we did a pilot project to try to shift the needle a little bit on something that's been sticking in the industry forever, is destructive testing of liners. So when we talk about testing of lining systems, two basic kinds: non-destructive testing, which is going to really just verify seam integrity. So you can see right here. So you have a dual track seam weld, and you can put air pressure in it and non-destructively test if it holds air. You know that the seam is integral throughout the length of it. A roll of 60 mil liners, about 540 feet long. So you get a pretty good bang for your buck on one test. And then the other being destructive testing. So that's for verifying seam strength. So if you're going to put a liner in shear, or it's going to have some kind of tension in it, you want to make sure the seam's not going to pull apart. The only way to test that is to basically cut it out. So and test it. And so therein lies the problem, is you built the system that you don't want not to leak. And in order to test to make sure it's not leaking, you cut holes in it to make sure it's not leaking. So there's got to be a better way, right? So if we go back, if we go back to where did all this stuff come from? If we go back to the origins of the early 80s, mid 80s, EPA passed some rules that said hazardous waste landfills needs to have a lining system, a double liner system. And at the time, it's really, if you really want some kind of hilarious reading, you look back through, just Google some of these documents related to geomembrane testing in the 80s. And the EPA was doing all kinds of things, research symposiums and summits and different things, and trying to understand every manufacturer was making a different product to a different standard. Every installation technician was a different, something different. There was people were saying, well, plastic will never work, PVC won't work, we like clay better, all these different opinions bouncing around until finally, 1987, Thomas Wright, who was with SES at the time in California, they wrote this bottom technical guidance document above, here's how you test lining systems. And that kind of became the Bible. After that, everyone just referred back to Wright and said, that's what he said. And actually, he didn't even say that. He just said, for example, it seems like people do wooden tests every 500 feet. So every 500 feet of seam, you cut a hole in it and test it. And that's, to me, it's kind of like, Ford doesn't crash test every 500 cars, right? They do it one, they have quality, and then you just go on with the program. So this is what everyone kind of went back and did. They said, oh, 1 in 500, let's do that. So, but really more interestingly, a lot of discussion about, the level of sampling really should depend on the complexity of the project, the variability that you're trying to overcome. If you're seaming in the wintertime somewhere, maybe you have to do more testing, or if you're seaming in somewhere that's very dusty or something like that. So this idea of removing variability was kind of key to the project for us. And if you look back at current practice, so one test in 500, it's to the point now, some regulatory agencies, I know Kentucky has it written into their law that says you shall test 1 in 500. There's no way around it. And like everyone, they want to raise the bar. You want to meet the standard, exceed the standard. So instead of cutting 1 in 500, well, let's do 1 in 450. Let's do one more often so that we're exceeding the standard we have. We make sure we have enough. And then what you're doing is you're taking this dual track fusion weld, very robust system, and you're replacing it with a patch that's basically hot glued back to and its destructive seam sample is like a foot wide by 3 to 5 feet long. So you cut enough of these things in the wrong places where water might be holding, then you've really done some damage to your system. So you're taking a superior weld, replacing it with an inferior weld. And then some CQA firms are very good about testing locations. They can test them high in the cell or somewhere away from, let's just take a wheel and say every 500 feet, I cut a hole. That doesn't matter if it's the lowest part of the cell, whatever, I just cut a hole. So the Geosynthetics Research Institute out of Drexel University, the Kerners, Bob Kerner and his son George now runs it. They wrote a white paper in 2003, so this is 16 years after the Wright paper, that said, how do we get out of this 1 in 500 business? I mean, we should be able to do better than that. So they, where they were, they had currently no value added. They postulated if you're having a lot of failures, you could close up the spacing. If you're not having many failures, you can make it wider. But then they sort of said, well, what if we just took this variability out of the equation? If we used, instead of, back in the EPA papers, they would, to do a liner installation, they would just go get people out of the unemployment line and put them on the field and go install a liner. So what if we used people that actually knew what they were doing, had certified technicians? What if we taped edges? Most of the liner seam failures are because of water or dirt in the seam. So if you can keep that seam clean, you've eliminated a lot of problems. There's now automated welding technology, which has been around in Europe for 20 years. It's just coming to the States. But that allows you to see data related to your installation. I'll go through that more in a minute. And then in 2003, they were looking at infrared and ultrasonic testing that kind of fell off the wayside. But we were really interested on this project was coming here to this, how do you get to no routine sampling? And so you do sampling based on just your trial seams before you started welding in the beginning of the day and observations. And that was what we, originally all the EPA work was, you just need people knowing what they're doing and looking at it in the field. And then if you're having problems, let's go fix the problems. So anyway, we started a pilot project, but get ahead of myself. So this is 2019, so 16 years after the white paper. The Kerners wrote another paper in Geosynthetics Research Institute in Geosynthetics Magazine saying, it's okay, it's now 19 years later. We're still stuck at 1 in 500. How do we get past this thing? So they documented all the advancements in the industry since the 80s that should say we're doing better than we were. And I won't read all these, and you can go look at them, but just to say significant advancements in the industry related to quality and repeatability and technology. So the 4 pillars I mentioned in the 2003 white paper, the first one, so this organization, IAGI, they do now geosynthetic certified technician licensing. Basically, if you're a technician, you weld different PVC or 40 mil or 60 mil or whatever it is, you send it in them, they test it, and they say, yes, you are certified to do this welding. We know that you've demonstrated that you can actually do the work. And the company also can get certified, saying that they can supply, they can train, they can do all these things related to welding. We worked with Agro-America to develop a different product. So they put a taped edge on this outer 6 inches of the liner roll, so that one edge is tape up and the other edge is taped down, such that when you shingle them, the taped edges are together. You can pull the tape off and keep the clean, right in front of the welder, so you're not getting mud and dust and dirt and everything else in the seam. So again, removing that variability. The next one, the automated welding technology. So we use this here, but it continuously measures temperature, pressure, and speed. So on this project, we measured it every 4 inches. So if you did have a destructive or non-destructive failure, you'd have some hope of going back and looking at the data and seeing, well, where did you have a problem? And it really gave the ability of the QC person, instead of running around just filling out paperwork, they could monitor the data and really look at where the issues were happening in the field, if there's a certain area that was a problem. And then the 4th pillar, electronic leak location testing, which really isn't that new as an emerging technology, but also research has come out to say that we do all this work on geomembrane seams, and very little of the failures or holes that people find in geomembranes are in the seams or in the sheet itself, because it was on a rocky substrate or something happened. This hole right here was on a project, one of our landfills. We found after Hurricane Florence, the leak detection system started going crazy. We had to excavate 40 feet of coal ash to go back and find that spot. And so that was enough to send us over our regulatory limit for leakage in the system. And we used electronic leak location testing to help pinpoint and find that spot. You finding that hole in 60 acres is not the easiest thing to go do. So, so just for example, what's the impact of being able to reduce destructive testing? So we looked at that same project that had the hole, and it was 60 acres, but we looked at 26 acres, so it was a phase 1 of the closure. And of just the 50 mil liner, there was 49,000 linear foot of seams. In those seams, they cut 167 destructs. And of those destructs, 54 of them were retests because there were failures. So, the 1 in 500 only counts if they all pass. If you have failures, then you're cutting more and more and more seams. So it ended up being an average destruct collection rate of 1 in every 293 feet. So we almost doubled the amount of holes that we planned to do. And it was 7.6 days for the average resolution. So you cut the hole in the liner, you send it off to the lab tests it, they send it back, you have to patch and do things. So the average was 7.6 days to resolve a destructive test and move on. And the long was 31 days. And this is what happened on the long chain. So the first destruct was cut and sent to the lab, it failed. So then you go 10 feet either side, cut more tests, and they failed. And so then you go 10 feet either side and cut tests, and they failed. And then you go 10 feet either side. And so it ended up, you basically just obliterated this whole seam, 80 feet of seam, and it took you 31 days to try to find. You had no data, you failed a non-destructive test, you have no idea where to start looking at this 540-foot seam for where a problem could be. So there's 31 days that the liner company was stuck. They couldn't put any overlying layers. No one else could do any work in that area until you had a good passing test result. So overall, for our part of the project, we were trying to figure out, can we, obviously less holes and less patches is a good thing, but also if you're doing the testing based on data, we should have a time and cost savings, because time is money. We wouldn't have, if you could put the next layer on, that same day instead of waiting 31 days. That's a good deal. And also the QA folks can spend more time looking at the production and the data and the quality of the work instead of, just running around, chicken with their head cut off, running down numbers so they can have the same numbers that the QC guy turned in. So what did we do? We picked a pilot project. We kind of hand selected our all-star team of folks. And so services was our general contractor. Chesapeake Containment Systems had done a lot of work already with data acquisition liners or welders. Agro-America, produced material for us. We worked with the North Carolina DEQ to give us a pass on the 1 in 500. They were excited to see people not do something cutting holes in the liner, but basically small landfill with a small 0.2 acre lined impoundment that had been built in 1992. So it was a 5-layer system. We built this pond in 2 days in December. It is North Carolina. It's not December here, but still, the temperatures were in the low 30s, upper 30s, and so you just wouldn't get 5 layers done in 2 days if you had to wait for destructive tests, and then weather comes in and different things. So the project specifications developed by Wood. Basically, it's just the four pillars we mentioned. You're going to have certified welding technicians, taped edges, data acquisition welders, and lead location surveys. And then instead of having a destructive test, they said, well, we'll just evaluate the seam. We can collect samples if we want to, but we don't really need to. We're going to look at temperature, pressure, and speed. And so the seam. These are the specs that we came up with, some research, but somewhat randomly. You can see the taped edge on the roll, and then this is the welding technicians that's pulling the tape off right in front of the liner, welding. Here's a picture of what the readout is on the welder, and it has alarms that are set. So that's also hooked up to Wi-Fi, so anybody anywhere can hook into the system and see exactly what's going on with every welder. This particular company, Chesapeake, their executive management gets alarms anytime a destructive test fails. They take it seriously. They want to know what's going on with the quality of their product. So at the end of the project, you get all this data, right? Thousands of sheets of data, as anyone knows from a CQA report. So what you have here on the left is the sheets. There's 4 sheets for every weld. And then on the right, this kind of represents the upper half of the sheet so you can see it. So some things we ran into. Every welder starts at 1 at the beginning of the day, and it goes to however many welds it has. So if you have 3 welders going, you have 3 weld number 1s and 3 weld number 2s and 3 weld number 3s. So that was something for QC guys to be aware of. They had to go back and say, well, weld 4 was actually between panels 4 and 5, and go back and try to figure out where all these things were. It helps that the machine has a starting and ending time, so they could go back and look at the data on the liner, figure out where things were. On the lower half, there were the tolerances that should have been set in the machine weren't. So here you can see the setting was NA. They forgot to set the welder. So that's something to check on, making sure that the setup equipment is right. The cold joining pressure was 280 pounds foot. So basically what that means is when you clamp down the welder, you're at 280 pounds. But as soon as the rollers heat up, it melts the plastic a little bit. You're going to drop down, and this project had dropped down to 210 pounds. So you have a cold seaming pressure and an actual welding pressure. So we went off the welding pressure, and so our threshold was, as low as 190 was okay, and as high as 230. And so what you see, second page, temperature, rock solid, never changed on any weld we saw. Speed, didn't matter, uphill, downhill, never changed, never a problem. In the bottom of the sheet, pressure was the big deal. The pressure sensors on the welding machine are so sensitive that they can tell if you're going over smooth or textured liner. I mean, it's to the micron that they're observing. So the CQA representative just had to come through and they say, okay, well, what happened in this area? They're in the anchor trench, or there was a wrinkle, or there's a T-seam, or something happened. And so the CQA technicians went out and looked at each one of these things and said, what went wrong? Is it okay for us to not cut a destruct? And so the third page of the project, it just shows, every 4 inches, you're gathering data, and whenever you're below, like this here, you're below the 190, it starts collecting data every 2 inches until you're above the 190, and then it goes back to 4 inches. So you very, granular information on where to go look for issues in the field. And then on the last page, it basically tells you, your minimum temperature and maximum temperature, where those happened on the seam, and, same with speed and same with joining forces. So at the end of the project, we had 71 areas to go look at as a problem. And most of those were acceptable because you're in the anchor trench, which is outside the containment anyway, T-seams that are patched anyway. So there's a very small amount of things that we go ahead to go look at and fix. And so we said, well, what happens if we went up to 20 pounds or to 40 pounds or even 60 pounds? At 40 pounds, we went from 71 issues to look at down to 15. And so kind of the recommendation, lessons learned, you can open up the window on the pressure a little bit, gets you a whole lot less things to look at and still have good seaming practices. So just some observations here. This again, anchor trench, he's got his hand on the handle, and that's where the pressure load cell is. So every time he picks up or puts it down, you're getting high and low pressures as you're coming across the seam. Good passing, non-destructive test. You can see very uniform welds here. A T-seam, just what it looks like, it's where you have a T. You got three sections of the liner coming together. You have to patch those anyway because there's no other way around it. So those you don't have to worry about. They're going to get patched no matter what you do. Wrinkles could be a problem, again, going up and over. You evaluate those. This is one we had that was a burnout or an off track where the material wasn't lined up quite right and it sort of came off track in the welder. That was caught. And so we could identify exactly where that happened with the data and go back and find it and cut it out. So at the end of the day, we feel like it's a successful demonstration of a data acquisition welding application. We didn't cut out any destructive tests. We were done with the project in 2 days. We do feel like you can open up the parameter somewhat to about 40 or 60 pounds. And then there were some logistics. The taped edges, as I mentioned, if you need to shingle them, you need to then figure out how you're deploying them. So you don't end up with an up to an up or a down to a down. And so that was a little bit of a learning curve there. Confirming the manual entry tolerances. So if you want to get the alarms right, if you want to get the data right to print out, you got to put the data in the machine properly. And then just some matching weld numbers. If you had multiple machines, multiple crews, it could be a little bit of a nightmare trying to figure out what seam went to what machine in what place. So next steps, Duke Energy, the reason we really did this project is Duke Energy was facing excavating 84 million yards of coal ash out of their bases in North Carolina and building 2,000 acres of lined landfills. So we wanted a way to do it more efficiently, better. So we looked at this, pilot project. And so that's where they are right now. They're in the construction of 3 new landfills, expansion of 4 other new landfills, and using this technology to cut less holes. So I just want to acknowledge some real good partners, and everyone came together within a year and kind of, we made new material, we made new rules, we figured stuff out, and very collaborative effort. And so successful at the end. So pending questions, really appreciate everyone's time here today and open it up to the floor.
Any questions? Yes.
Yes.
I got 2 questions for you. The first one is you mentioned the electronic seam testing that you found the small hole,
Right.
I think after the hurricane. Is the electronic seam testing, is that part of the operations? Is that a regularly scheduled thing? Or is that just because of the hurricane happened and then you went back through and tested?
That one in particular was just because of a hurricane,
Okay.
but in general, for this project, it was set up to test the secondary membrane, basically the last line of defense to the environment during the project construction. So you almost have to design for that system to be able to be effective, because if you don't have the right grounding and different things, it doesn't work very well in advance. So.
Second question too, did you ever figure out what the cost savings may have been through this way rather than the conventional?
Yeah, we're looking for full-scale testing, but we worked out that a destruct costs about $500 in money, in time, and then about maybe a week in time. And so if you have tests like that one section I had, that 167 destructs, $500 a piece, you're saving some money, but the bigger thing, all the systems that are going to be built on these facilities in North Carolina, they're all double-lined leak detection. So you've got 6 layers of geomembrane. If you don't have to wait a week between each one, then you can cut months off the project. So savings there. It's in front.
What does the term burnout mean?
A burnout basically is just that the welder might have got stuck or hung up or slowed for a little bit, and there was too much heat for too long a time, and it burned through the liner. So you're looking for that hole from a burnout. So it's in the back.
What was the additional cost for the taped edge?
The additional cost of the taped edge, it's about a penny to 2 cents a square foot. And so on a roll of liner, it's $400 to $500 on a roll. So there is some extra costs and those sort of things, but again, not having the destructs because of that, you know you're keeping it clean, you've removed that variable. So, anyone else? All right, well, thank you very much.
All right, with our next talk, legacy mine drainage considerations when using enhanced evaporation as a control tool. This is done by Bob Ballantyne. Bob served at the United States Marine Corps. He's an electrical engineer, and his follow-up education concentrates on molecular and atomic spectrometry. Spectroscopy?
Spectrometry will work.
Okay.
Everybody screws it up, so it's fine.
Yes. But with that, we're running just a couple minutes late, so we'll get right into Bob's talk, and thank you, Bob.
Thank you. I'd like to thank Tetra Tech for an excellent party last night. Everything worked out well. Until I got to the second floor escalator, it was not working last night. So I had to do a high angle rescue after the lady insisted maintenance was not going to make the escalator work. We started this a while ago when 40 CFR 51300 was promulgating through. We realized that there was going to be some problems with converted snowmakers, and the way we were mechanically enhancing evaporation by adding surface area without any regard to droplet size, droplet destabilization. Those of you who've been coming here a while, I think I did the first presentation on the early research in 2012, and we've continued on. We now have viable products. I assume you know that. I'm really here to go over a bunch of the research that we're doing to continue to improve and push the state of the art. Basically, droplet destabilization was the biggest problem that we had. You couldn't get consistent droplets with the destabilization. They would dry out in flight. The ion content would compound out, and then you have a pollution plume with a sedimentation rate of less than 66 minutes for a 10-foot drop. We're doing this next section because I started finding interesting stuff. This happened to come from a regulatory agency in South Carolina. They wanted to know, is this true? I've blocked out the name of the competitor because it would be not right to say that Neptune did this. So now that they're protected, this was actually a real question. They wanted to know, will the chemicals fall out and magical water vapor go up? I told them, I don't know. I've been to school for 12 years in the separation sciences. We've got RO, double distillation, nanofiltration, and microfiltration. And I think I got ripped off because all I had to do was fly it in the air and it would magically separate. So it made no sense at all to me. So we've been back at it now, doing a little more science so that state regulatory bodies and federal regulatory agencies have a way of getting a better grasp. The regulatory agencies often have a problem in that they're asked to understand an incredible broad area of science that they may not have any training in at all. So we've been pushing it forward. You've seen this picture before if you've been here. This is our 75 horsepower machine where we were proving that we had pollution problems. Basically, as long as there's water there, the plume is not going to go below wet bulb, as long as there's water in the plume. As soon as you see it go below green in this instance, there's no more water in the plume. What I've mixed up here is a brew of 50,000 TDS, sodium and potassium chloride, and I'm blasting it up into space with the machine we obsoleted about 5 years ago. So that the light blue that you see in the plume is a reflection of some of this solar energy behind me. And this is really all droplets well below 10 microns. So in a dead still wind tunnel, when we drop a 10 micron droplet, 66 minutes till it touches the ground. Out in the real world with updrafts and downdrafts and civil features, you have no idea where this is going to land. And we had basically already proved that with the acid rain problem in the Adirondacks, which led to many of the Clean Air and Clean Water Act rules. Things a little touchy. Anyway, problem is, can't have droplets dry out in flight. If you've watched this before, high-speed photography, T plus 4.7 milliseconds, the droplet's already destabilized. T plus 7 milliseconds, the droplet has primarily fractured. This is pushing at about 71 miles an hour. T plus 10.3, the medium droplets have re-destabilized, and by T plus 15 milliseconds, what we have here is a 150 micron droplet that's now somewhere between 58 and 88 particles, all less than 10 micron. This is a pollution plume problem. This puts future shareholder value at risk. Somebody's going to figure this out. You will get away with it for a while, but eventually trees will start to die, grass will turn brown, and somebody's going to start going upstream to find out what happened. The solution was simple. We talked about this about a year ago. We started to monitor the ambient temperature and the wet bulb temperature, which gave us the evaporation that could take place. We know the trajectory, and we know the thermophoresis loss to dry air, so we know how fast the droplet will evaporate. By sizing the droplets correctly, using VFDs to change pressures and air flows so that we can change trajectory in the event of crosswind or tailwinds or headwinds. This allows us to control and make sure the droplet lands back in the impoundment and keeps the pollution plume, the ion content, where it needs to be, which is not out in the natural world, but in an impoundment where we can handle it correctly. We had to do a little bit more work this year because we started seeing some of these crazy things. That, just so you know, the earlier non-science article was also copied by 3 other people who have these big trajectory evaporators, so it started to spread rapidly. So I have a team of interns. We don't use them to sweep the floors. They get to do real science. Kirsten has been with me on her 5th year now, and Patrick and Caden have been with me 3 years. And they built the wind tunnel for us to do this year's studies. We were interested in monitoring ambient temperature, the control of the dew point, velocity, and turbulence studies. We're using a Vasali monitoring system. We print everything out on the 3D printer to make all of our instrumentation fit the wind tunnel. We can go up to 20,000 CFM with this wind tunnel, and we monitor everything in real time. It's all logged. I do make them read. In this case, Caden kept asking me questions, and he was really starting to annoy me because he's a sophomore. He should be able to do this on his own. So ended up giving him the boundary layer theory and told him, just read this and you'll understand it. So he would sit back there running these tests while reading boundary layer, and he comes up to me at the end and he's like, I'm going to be a chemical engineer, and this seems to apply. I'm like, you think, huh? Yes, pretty good. Anyway, we had a good time. We have a pretty good time with them. He also copied the beer taps that we have in the back, and that's how he made his money last year. His father was very proud of the things that I taught him. This is how we were deciding. So we're doing a bunch of studies right now on surface tension, bioslime as well, and how humidity, dew point, and flow all affect the evaporation rate. We've found a lot of problems with the Penman equation. We have some serious problems with the Shuttleworth equation. We hope to publish in about another year and a half the updates to those. They have some problems with their solar radiance. They're not paying attention to the infrared spectrum. Did my medicine go bad or? Okay, just wondering. Making sure, I have to check once in a while. I might have to call the hospital quick. Sometimes it gets out of balance, it gets a little weird. Anyway, we're using gas chromatograph needles. We weigh them before, we then inject, and we have the needle hang on to the droplet through surface tension, and we run a certain amount of time, then we pull the sample back up into the needle, reweigh it on a 6-position balance. And this is how we're collecting the data of what goes on. We're using Illumina to control our hydration down the line, and microspraying fog nozzles to set up the humid conditions that we're looking for at 20%, 30%, and 10% in different ways. We also do a lot of studies on what causes droplets to collide and how did they move around. We do that in the wind tunnel as well, with different speeds. And for us, the reason the ball is on a 3D printed hanger is we use different colors because we also have infrared sources, and we put different temperatures inside of our wind tunnel as a black body source, but not a true black body source, not up in the Kelvin range, but so that we can see what happens as a droplet passes by a source of infrared energy that can cause it to change temperature. It's been some very interesting work. Not so much for us. Evaporate wastewater is pretty simple now for us. But the paint industry has been by. We have a lot of people that come and talk to us because we do weird stuff. Did a big study on droplet collision this year inside the tunnel, looking at how on impact, up until this point, everybody thought droplets mostly coalesce when they smack together. What we found is that doesn't happen very often. They bounce off of each other and they shatter, both shatter. One bounces, one shatters, all kinds of wild ways. So we did try and group what was going on with the droplets, mostly again for our own information so that our PLCs can handle pressure, droplet sizes, and what kind of daughter particles we could be making if we get the energy levels too high. So everybody likes to see mine pictures at this conference. It's the best conference we have all year long. I love coming here because of all the different projects that are presented real world data. So this is the Kinross site in Republic, Washington. They were having a lot of trouble. We ended up taking care of the 65-acre tailings pond using a trajectory version. I like this picture because it really shows the sedimentation rate of the droplets. You can see the mountains clear behind it. We know we don't have a pollution plume problem. We're not losing control of the ion content, and they have great telemetry here. They measure everything. So we know the pH of the pond, we know the TDS of the pond, we know that we're concentrating the ion content because the TDS is following the evaporation rates. It's been a very good program. It's coming into its 4th year. They have like 30 units now. They had 7 when we started. This was the 2nd year up there. We have 45 horsepower moving 7.1 million gallons per month, roughly 22 acre feet per month, under a controlled situation in an area of the country where it's rarely above 78 degrees and the humidity's up usually around 56 to 60. This was part of the proofing that, look, you can evaporate all the time. Just depends on how much surface area you have to create to take care of the problem. Now, it cannot pencil out in some points. It's very difficult down in Mexico and Central America to make any of this work. If you want to follow our EPA's rules, they make it work, but in different ways. They just blast the crap up into space and let it float out into the ocean. I mean, they don't think they're doing that, but that's what they're doing. So then we came out with a downdraft evaporator. This was for a project for U.S. Energy Fuels. They have impacted waters that are very close to public lands and some national forests. And so they needed a way to evaporate, get the trucks off the road, take care of the mine drainage and the stormwater on site. And so we started the downdraft evaporator, I don't know, 4 or 5 years ago. Research continues on it right now. What we're finding out is bioslime in ponds really cuts down the evaporation rate because it's a surface tension thing. But we're using an AM modulated signal and we're killing it. And what we're finding is we can kill the biologicals with the AM modulated signal, and we are clumping together the ion content. It's creating a skin effect of about 4 inches of halfway decent water quality on the top 4 inches. So we have been able to take and increase evaporation rates with this method by 30%. Now that's very preliminary work. If I'm here in 2 years talking about it, it means it all reproduced itself this coming summer. If I'm not, it means it didn't work out very well. I had some problems with the data. This is the Energy Fuels site. It's up in Williams, Arizona. It's actually up in the mountains outside of Williams, Arizona. Nothing comes off. Trucking was expensive, but the deposit is worth a lot, and so they wanted to protect the deposit. Got called in acid drainage in an old bentonite mine in NOV. Almost everybody knows NOV has the old bentonite mine. I kind of ended up with it in an acquisition where the due diligence may have been slightly lacking. So this thing was draining down into state's waters. In Nevada, the state obviously was not happy. Regulatory bodies there's no infrastructure up there. So because one of the things we ended up with about 4 years ago was a patent, the first patent in a long time on an airfoil, we were able to take what used to take us 25 to 40 horsepower and accomplish that with 3.3 horsepower. What this has allowed us to do is operate in areas where there's very limited infrastructure. It allows us to run off of wind turbines. We put the wind turbines in for NOV this coming spring. And this will be the first time we take care of orphan drainage, 100% renewable energy. They were really into the power panels for some reason. I like the wind a lot better. At least it's more stable for me, and it doesn't require the maintenance. You got to clean these panels all the time, and I know there's people that make it work, but it just seems like an awful lot of work to me compared to putting an eagle chopper up and just making all the power that you want, you know? So that's kind of, well, that's what it does. I mean, we can all pretend, but we know what it really does, right? Well, I guess it lost out on 2 slides somewhere. Well, we're supposed to be a little further along here. Let's see, what was I lying about? I was lying about the eagle choppers. Okay, yeah, so it's site it works where we need to be. We'll just leave it there. So site it works, remember, we don't really, this thing's blinking and stuff, or is my medicine all messed up again? Okay, no problem. I'm just making sure it's not me, you know, I need to report in. So, site it works. Basically, we're not really doing anything. We're just pushing the state of the art. So I don't want you to think we're up here smart people inventing stuff. We're just copying work that's been done back as far as the Federal Weather Bureau in the 1940s and kind of understanding it better, pushing it a little bit. We have a lot more instrumentation available to us than some of the people did back then. So it allows us to, I'm telling you, you're trying to get me to do a seizure, right? Anyway, so Michelle in the back, she has copies of the paper. If you really want copies of this stuff, give her the business card or give it to me, and we will get you copies of the paper. And thanks for your time. Appreciate it. Love this conference, and I think it's time for break now, unless you have questions.
Bob, thank you. Do we have any questions?
Yes.
Yes.
affected the chemistry, like variability in ion concentration or effects on the evaporation rate?
Yeah, the question is, have we done any testing on ion content, concentration, and evaporation rate? Yeah, we have, a lot of it. TDS, about 5% at 20,000, about 9% at 50,000, and that doesn't matter whether it's chloride or sulfate. And there was one other one, pH. On the low pH, it really starts to hammer once you go below about 2 to 5. We don't get very good evaporation rates. We're using this AM signal to see if we can separate the water and concentrate the acid even more just below the level. The only thing that was really odd in all of the TDS studies was, so you keep losing efficiency all the way to 160,000, then 180,000, and it just keeps diving off until you're about 24% below what would be a normal water evaporation rate for the same conditions. Then at 200,000, we thought, well, yeah, this is really going to be terrible at 200,000, and it went up. Well, it went up because all of a sudden it's separated by weight. So we had this layer on top about 2.5 to 3 feet, which would be 1 meter for those of you from Europe, and of water that was only about 50,000 TDS because of the separation. And we really saw it first in Hobbs, New Mexico. We were down there doing a drill cutting separation facility. It was terrible, but we had superheated the water with the sun. So we were up around 108, 110 degrees F. And we were way over the top, 250,000, 260,000 TDS, and it cooled off, and the whole pond dropped. Like it was just, so they loved it. They went in there and excavated all the sulfate out and continued to use the pond until we eventually decommissioned the pond about 2 years later. But that's what we've noticed, that TDS is a real problem, and then we don't really have enough data. We know the bioslime's a problem. It's about a 30% reduction. We don't have enough data yet to really understand how the bioslime is affected with the constant air movement across the top of the pond, because the downdraft evaporators are designed to push 20,000 CFM across the boundary layer at all times. And then they're designed to make ripples so that the pond surface area becomes a lot larger. So we'll have that data in another year or two. We have data, we just haven't repeated it yet. Anybody else? Thank you very much. Appreciate your time.
Thank you. Meat and the potatoes of our conference, and that is our talks. So our first presenter is also a longtime participant of the conference. Lisa and her group have presented countless numbers of presentations. We were just during the break talking probably 5th or 6th of her talks alone, which is also a product of why we keep bringing her back, because on the evaluations, people are asking for her. So we definitely appreciate Lisa and all of you've done for our conference. But Lisa will be talking about microbial reduction of nitrates and selenium in mine-affected water using saturated rock fills. Lisa Kirk, who has earned a bachelor's in geology and a master's in aqueous geochemistry and a PhD in ecology and environmental science, has worked in Montana for over 30 years as a professional geochemist, and she has an excitement about her work that is truly raised the bar for everyone who she works with, and that's one of the real powers of Lisa, and is her commitment, it's her enthusiasm, and I just want to say thanks for always being here.
Thank you very much. That's very kind. Thanks for being here today. Thanks for those of you who are online joining us for this presentation. This title is probably not as exciting as it should be, or doesn't reflect how excited I am about this work. This is 20 years of my own work. This particular case study reflects a decade of work with our industrial partner, Teck Resources. here I show Dr. Seth D'Imperio, who is here in the room as my co-author, but Ethan Wilogo is here in the room, Joe Lazarus and Lexi Gilbertson are here in the room. These people all contribute to the work daily in our laboratory on these reactors that help us to understand how and why native microbes will remove nitrate and selenium from mine-affected water. My research began in Southeast Idaho as part of my doctoral research at Montana State University. Dr. Brent Payton, my current collaborator, my former mentor, is part of this work as well. So we're very excited to tell you about SRF technology. So this talk will provide a bit of an overview of microbial ecology and metabolism. Don't worry, not too heavy. It's going to be a little science light, but with a focus on nitrate and selenium reduction so that we can talk about how this saturated rock fill is designed to facilitate the process we're looking for. Specifically, we're going to talk about the saturated rock fill, or the SRF, that is in situ treating nitrate and selenium in mine-affected water using mine waste. A subsurface reactor that's about a half a kilometer long in British Columbia in the Elk Valley. You may be aware that there are concerns about selenium release from those 5 mines that Teck Resources owns and operates, and that selenium is a concern in terms of bioaccumulation for Lake Koocanusa. So this is not just a problem in BC. Oh, you put it on this thing. I'm sorry. Sure, can have it.
Would you mind clipping it to the top of your blouse?
I will try. You want to hold on to that? Sorry, we're having technical difficulties. They're going to redress me here. There we go.
Perfect. We should hear you much
Thank you. Sorry for that. I get talking and excited about this, and I'm not aware of the problem. So this in situ bioreactor was constructed in order as a pilot, as a demonstration trial of this technology. They began work in 2017 in January, the coldest possible part of the year to commission a bioreactor in BC. But as I was pointing out, this is an issue that affects Montana as well. More importantly, and this is where I get very excited, this technology affects more than just Teck. It affects a lot of the mining industry. And the reason for that is because mines, it turns out, manage the products of microbial metabolism all the time. Biogeochemical processes in industrial water, it's not just mining, we've heard from the power sector here at this meeting, those processes directly affect nitrogen, they affect sulfur, and they affect metal solubility. Well, other than dust, what other problems do you have at a mine site, right? Those are all important to mining operations. The microbes influence solute release and attenuation. They are directly involved in scale formation and biofouling, and they influence our testing paradigms. How many of you have run a humidity cell kinetic test? How many of you know what the microbes were in the kinetic test? Kind of hard to believe that we do that many humidity cell tests and don't understand the main players in controlling reaction rates in these environments. Most of the metabolism occurs within an attached biofilm. So this picture of this guy fishing here is to kind of key on the experience we've all had of stepping into a creek and slipping on a rock. That's a biofilm. Microbes use biofilms to locate themselves in a flow field. Food comes to them, wastes go away from them. It's a neighborhood. It's an ecosystem where you have aerobic organisms and you have anaerobic organisms. You may have organisms that cycle iron and sulfur and selenium and nitrogen. So we get pretty interested in the ecology of that microbial community as it influences biogeochemistry. And I really want to share my enthusiasm for Paul's talk earlier, because these systems, these biological treatment systems, whether they've been active or passive, have in many cases been treated as black boxes. We put carbon in, something good happens, and everything's fine until whatever good was happening stops happening. So one of the things that we consider pretty important is the thought that if we don't know how it works, we can't fix it when it's not working. And a couple, 3 times a year, we get a call from somebody who says, hey, this was going great, and then we had a freshet, and we had, all of a sudden, it's not working, can you help us out? And our first question is, well, how did it work to begin with? So it's important to understand this ecology because it's doing the heavy lifting. You know, for tech, this is replacing a lot of active water treatment very successfully, but if they don't understand it, and I had a colleague point out that this is a very heavily studied, well investigated demonstration trial. Well, that's a credit to tech as an organization. They're very thorough and they're very cautious. They're good at risk management. But the truth is, we need to know what those little invisible germs. My colleague from Southeast Idaho is here, Rob Klein, Dan Klein, sorry. And I remember when we first started talking about this down there, one of the guys on the site sent me a picture. It was a cockroach in a core box, and he said, hey, we found the bugs. We found those bugs you've been talking about. So it's important to know how it works. Whoop. So there's a lot of factors that influence the metabolism, sorry, I have shaky hands, metabolism in those attached biofilms. The biofilms can attach to various minerals. This is from a textbook for microbial ecology, kind of the Bible, Brock, if you're familiar. The amount of organic matter, the amount of water, the amount of air, which electron acceptors are present, because that's what's going on, is these organisms are transforming oxidized forms of a particular we keep it simple and say iron. Oxidized iron, iron 3, converted to iron 2. Interestingly, there's organisms that'll take iron 2 and convert it to iron 3. And they all live in this little environment, right? And what we're trying to do is shift the ecology in that pore space to do work that we need them to do. So they're not doing it to help us out. They're doing it for one of 2 reasons. They're doing it to make energy, or they're doing it to clean up their own environment, to detoxify their own environment. So think about this neighborhood. Think about this biofilm condo, right? There's aerobes on the outside. There's anaerobes on the inside. In the middle, there's a mix of facultative anaerobes. Maybe they're breaking down hydrocarbon and making it available to the guy next door. Maybe the other organism is consuming oxygen to make it a less aerobic environment. That makes it possible for a different organism to kick in. So there's all these processes happening concurrently, and they're all kind of synergistically taking advantage of the niche conditions that exist within the biofilm and within the environment, which could be a waste rock dump. It could be a saturated rock fill, which is what we're talking about here today. It could be a hydraulically bulkheaded mine, as Katie showed us yesterday. So we like to think about biofilm as an ecosystem, and we need to remember there's competition, there's symbiosis, so these guys handing off resources that are needed. And these organisms are adapted to life at the edge, to living with very little food or nutrient, to growing very slowly. So they are much better at stressful environments than we are. Another thing to think about is how quickly the oxygen gradients that influence organisms develop. So this is rough. This is sorry, I'm pointing the wrong way. Maybe a centimeter across soil clump. And you can see that the outside is fully aerobic, 21% oxygen, and the interior is fully anaerobic. So the gradients that get established that allow for diversity in microbial communities happen over very small distances. So the conversation with tech went something like, are you telling me there's microbes in that mine waste that we can use to treat water here? And if so, they were kind of not sure they believed that initially. How do microbial communities influence that in situ water and geochemistry? And what excites me the most is how do we use design to create the conditions that allow the community to control water quality? So we hear a lot about bioremediation. Years ago, we did it because it was inexpensive, right? It was like the last ditch, okay, let's try some microbes and see if we can solve a problem. But the reality is this should be integrated into our design process. We should be doing this up front and throughout the mine life so that we don't have to go bring pump water to these treatment systems. Oh, I want to tell you about this. Daryl Shuttleworth was part of our team, and he drew all these great graphics. This is not my art. I'm by no means an artist. Here's some elk on the side of an end-dumped slope of waste rock. You see that there's coarse rock at the base of this end dump, and then progressively finer material as we go up in the dump. That's because we have gravity sorting when these materials are dumped. And so these are very large, very steep facilities that they are trying to manage in terms of effluent. So you can imagine capping might be challenging in that kind of an environment. And these facilities have already been created. So what we landed on was a saturated rock fill. And we did that by recognizing that these steep dumps often end up being placed into mined out panels. And we had evidence from several of those mined out panels that the selenium was missing when the sulfate was still present. So what happens in these systems is pyrite is oxidized and sulfate and selenate are released together. The sulfate's persisting because things have to be extremely reducing to have the sulfate go away. We talked about that yesterday in Steve's talk. And so we know there's mine effect. We can see that that's still true, but the selenium's gone away. Well, where'd the selenium go? Well, it was a saturated rock fill where that occurred naturally. Now, typical of mining, the enthusiasm is to, well, if that's working there, then we have more water with selenium, we can bring it over and put it in there, and we can treat it there too. So Teck commissioned this in 2017. The initial capacity was 10,000 cubic meters a day. It's currently between 20 and 30, I believe. They've added a second phase. Influent chemistry was approximately 30 milligrams per liter nitrate nitrogen, 100 micrograms per liter selenate selenium, but that varied because we were taking water from an adjacent mine pit and pumping it to the SRF. So, spoiler, 95% reduction in nitrate and selenium in situ. So I want to just show you some of the dimensions here. So here's the injection well shown in green. We have monitoring well array 1, so there are 4 wells here, and then another group of wells, the second row, shown there. And then we have pumping wells. So water is injected here, and then it's removed here and discharged to a buffer pond, which allows Teck to ensure that they understand the chemistry of that water before it's discharged to the environment. So the water is moving through this flow field. You can imagine, I just showed you how that rock is end dumped. So this water's flowing through some portion of what had been end dumped material. So there's variable porosity and permeability. There's some local preferential flow channels. And so it's been an interesting process to understand the hydrology and hydrodynamics of the system. Whoop, went too fast. I've circled 3 wells here because I want to tell you about them in detail. I could tell you about all of these and we could be here for all day, and anybody wants to do that, let me know, because we love to talk about this. But monitoring well 1, monitoring well 5, and monitoring well 8 are the 3 that I'd like to focus on. I want to remind you that we're at this big facility. We're going to treat water in. We're at the mine scale. This is a full-size facility, 0.5 kilometer long and about 200 meters deep or more. But remember that the process that's driving the story is happening in the pore spaces. So this little cartoon, also drawn by Daryl, shows us some maybe selenium that naturally occurs in the pyrite, or maybe we had some gypsum or the selenium was sorbed on the rock. So there's our source. We have water moving through that pore. In this particular case, we've got atmospheric oxygen present. So what happens to the pyrite? Well, it oxidizes. We get sulfate in solution and selenate. Because this material's blasted, we have nitrate and some ammonium, right? And then we may see oxides. we may see gypsum, depending on the chemistry. In that biofilm here, which he artistically drew, we have the red organisms, which are aerobes. They require oxygen for metabolism. And their primary benefit to us in this system is to scrub that oxygen out, to remove the oxygen, so that the facultative anaerobes, shown in green, and the true anaerobes who live down deep in the biofilm, away from any oxygen that's up here, are living, and they work together as a community. So they influence the selenium, the nitrate, and also iron and sulfate concentrations. Don't panic, this is complicated, but it's got a lot of good information. So selenate has multiple redox states, selenium. As selenate, the most oxidized form, it persists in neutral pH water. It's available to be transported. Selenite is the somewhat more reduced form. It can sorb to surfaces, so it can be removed from solution through sorption. But it's also available for biological uptake. The more reduced we get in the system, if we stop at elemental selenium, that's an insoluble mineral, and that's kind of the holy grail. Selenide, which is basically where we started with the sulfide and the selenide, that's useful too. But what we don't really want to do is get to the methyl forms of reduced selenium. So in the case of this saturated rock fill, you can imagine when we saturate, if you were to take a jar and fill it with rock and sand and then fill it with water, as you fill it with water, you displace gas, right? And so in this case, we're going from having air in the bubbles to less air in the bubbles to no air in the bubbles. Now we know there's still oxygen in the water, but it's much lower concentration. So we have selenium that can be reduced. We have a system where, as we flood the system, we're having less oxygen available all the time. And interestingly, we can find the CO2, and that influences the alkalinity, as we've been hearing about sulfate-reducing systems. The organic carbon available in Teck's metallurgical or steel-making coal deposits is an interesting part of this story. One can imagine that in that saturated fill where we saw that the selenium had been reduced without anybody's help, they had some form of carbon to do that. And we think it came from the coal itself. But in the case of the SRF, we're transporting 10,000 cubes a day for treatment, and now more. And so obviously there needs to be a bit more carbon provided. So I like this conceptual model because it helps us remember that we're changing the oxygen conditions. In order to change the redox state, we require some form of organic carbon. And then over here, we need to note that these are the competing electron acceptors. So conventional theory would say all the oxygen needs to be gone so we can start on nitrate. All the nitrate needs to be gone so we can start on selenate. All the selenium needs to be gone so we can start on iron. In reality, these processes all overlap. But nitrate's a big one, iron's a big one, and sulfur's a big one. And the reason for that is that they have a lot more mass and they require a lot more energy for transformation in these systems than trace quantities of selenium. So if you're the person trying to design this water treatment plant, you're really worrying about the nitrogen in terms of cost and size of facility and some of those issues. In our experience, we see concurrent nitrate and selenium reduction. Katie told you about this. At Environment, we're keen to open the black box, and we use the tools of biotechnology to do that. So we're careful with our sampling. This was a sonic rig. We're very careful to collect samples aseptically so we don't contaminate them. We extract that DNA, we amplify it, we send it to an outside lab for sequencing. There is down gradient processing of those data. And where we end up is, this is an example from that drill hole. These are depths here on the left, and this is an abundance scale showing the relative size or the relative abundance in the community. And you can see that there were sulfide oxidizers present throughout, but this was just a drill hole in waste rock, wasn't a reactor. There wasn't much in the way of sulfate reduction. There were iron oxidizers and reducers, denitrifiers, selenate reducers, selenite reducers, and hydrocarbon degraders. So the community looks like it can do the work we need it to do. This is our baseline. So the saturated rock fill technology that Teck is using now will be at multiple sites, is designed to address nitrate and selenium in mine-affected water. These are backfilled mine pits. So this is the end dumped material that I showed you earlier. And we have pore spaces saturated with water, and this is stratified. So conceptually, we have an anoxic zone, a suboxic zone, and an anoxic zone higher in the system. Teck created the well field that I showed you, injection wells, monitoring wells, and pumping wells. And they really did a first-class job of it, by the way. Really great. When I saw the fiber optic cables, I was like, whoa, this is a pilot, guys. But it's actually a full-scale facility, and they now use it as one. So nitrate and selenate injected into these injection wells. So here's your nitrate, your selenate. We've still got some oxygen in the system. We're trying to pull that water through by pumping to the buffer pond. We need to add carbon. In this case, we're not doing bugs on booze. We use methanol, so I don't think it might be blind bugs, you know, I don't know, down in the dark, right? No. Anyway, methanol is the preferred substrate for growth, doesn't freeze, inexpensive. Introduced here so that we have the aerobic organisms consuming the oxygen. So this oxygen starts to go away. It supports the growth of nitrate-reducing microbes, and I've shown those as these little yellow guys, so you see them kind of showing up in the reactor. Nitrate is reduced to nitrate is reduced to nitrite, an interim transient product. The goal is nitrogen gas, which we breathe in the air every day. It's possible in a very reduced zone, you might get some ammonia. And so this is the transformation of nitrogen. Selenium, remember we've got all those different valence states, but we're really targeting converting selenate to elemental selenium. Different group of organisms, as I've shown it here with the little brown microbes. But the truth is that there's overlap in function. Some of these organisms can do nitrate and selenate and iron and sulfur. They're pretty talented, actually. And so the goal is to, the goal is to reduce that selenium. So let's look at results. So here's that influent chemistry. It was varying between 10 and 30 milligrams per liter. We had very consistent effluent concentrations, less than 5 milligrams per liter. This is just the first 21 months of the study, 65,000 kilograms of nitrogen were removed from the reactor. Selenium, we see the variation in our source term, but we see a nice, consistent, robust, I would say, and resilient in response to Frechette and various action or events removal, and we have somewhere around 350 kilos removed. We instrumented this well field with biocoupons. They're little steel cages. We fill them with sterilized rock, and we attach them so we can deploy them and retrieve them, so we can pull these out over time and see how the microbial community changed in response to operations. This was the baseline community. We like to do things in replicate, so we have monitoring well 1, I mentioned to you, 5 and 8 here. And each one of these bars represents a genus that has a function that we think we understand pretty well. So the baseline community was dominated by, yes, nitrate reducers, selenium reducing organisms, sulfate reducers were present, facultative hydrocarbon degraders, iron cyclers. And so we're just pointing out that between these 3 locations in that well field, before methanol was added, there was some variation, but the same organisms seemed to be occupying similar niches. Once we started putting carbon in the system, here's our startup time, 3 months and 6 months. This is for monitoring well 1 only. We saw a shift to an organism called Methylotenera. Well, it oxidizes methanol. We're feeding methanol. It also reduces nitrate. So perfect player. You'll notice that it wasn't really very obviously abundant in the baseline community. By feeding, we've shifted the ecology, we've pulled forward this particular organism that's of use to our goals. There were shifts in other organisms as well, but I'll keep moving. Because that was the relative abundance. That's a point I want to make. This is relative abundance. So these all total to 100%, and this is 20%, and this is 15% of the total detected taxonomic units when we did the sequencing using the 16S DNA. But we know that there might actually be more biofilm once we fed it, right? That kind of makes sense. So the absolute number is different. So when we look here, we see that the absolute abundance of methyl of Tenera at all these locations increased over the first 6 months. We see that Dichloromonas, although it seemed to decrease in relative abundance, is actually present in an increased actual abundance. And that's really important because Dichloromonas is a pretty heavy hitter in this system, does a lot of important work. Selenium reduction, nitrate reduction. We see that the Pseudomonas that was present early on has declined. It's getting outcompeted by his new buddies there, Methylotenera and Dichloromonas. Tech has demonstrated the success of this technology mostly through monitoring, a lot of monitoring. This system is incredibly well studied. There are samples collected initially weekly. I think, are we down to monthly? Perhaps not. Whenever there's an operational change or a concern about whether the dosing is right, a series of monitoring has been undertaken. We've done a lot over 4 years. Every 3 months, we've characterized this microbial community to understand how it responds and changes. So Tech's demonstrated that this is a viable approach to nitrate and selenium reduction and stabilization at the full scale. Now, what is really cool about that is they're using their waste rock to treat their water. So they have this opportunity to build their mine with this in mind, so that they have these opportunities. 80% reduction in capital costs, 50% reduction in operating costs relative to active water treatment. But the parameters have to be monitored, right? These are live reactors. So carbon and nutrients, making sure there's sufficient residence time for these processes to happen, limiting the formation of nitrite, that interim form, NO2, which can be an inhibitor. We don't want to see those organoselenium compounds, and it turns out that we don't really. This system is slower, it's more resilient and more robust. We want to reduce the biofouling. You can't eliminate it, but we want to avoid having those wells in that field plug up. And we want to optimize the function of the community through the addition of nutrients and so forth. So Tech has been a tremendous partner in this research. We have been very fortunate to be part of that work and to continue to support their assessment of this technology going forward. And I'll happily take questions. Oh, one more thing. Huge project team behind us. So this was the mining project team at the CBE and Brent Payton's lab. Many of the postdocs and students who worked with us early in this process. This is our environment team almost 2 years ago now, and we're going to update those photos soon, but many in our lab have participated in that. And then we're part of an even larger R&D team. So Tech, in its wisdom, brings together a lot of people who have a lot of things to contribute. SRK is involved, the CBE, University of Saskatchewan, Hendry Geosciences. So here's a picture of our group at the mine site working on the project. So now I will take questions. If we have time, I probably have gone over a bit. Dan's got a question.
So this is a great example of the nitrogen and selenium reductions. Do you envision or have you had ideas of this technology or these bioreactors being implemented for other constituents in metals, for instance?
Yes.
How can this be applied, or can it be applied to other constituents?
So uranium is another metal that, when it's reduced, becomes less soluble and forms minerals and precipitates. Arsenic will soar, but it's happier to do it when it's oxidized. So the reducing system might not be its target, or work so well for that. But we've heard a bit this week about sulfate reducers. So you could envision using the same system to drive to a sulfate reduction endpoint. We are studying that. And then it has relevance for any metals that would react with sulfide. So zinc, copper, lead, nickel, cobalt. So those metals as well. So thank you. I think it does have a lot of interesting potential. The other thing is, one other thing we're working on is the thought that this doesn't have to happen only when things are saturated. What we need is low oxygen. Nitrate reduction doesn't need a fully reduced system, neither does selenium. If you want sulfate reduction, you do need to really drive that reduction. But what if we could build waste rock dumps so that we accomplish that reduction in the dump itself, so we're not collecting the rock that's affected? Now, that doesn't have to be an anaerobic dump, but it has to have some transition within the facility to drive the reduction. So that's a thing that I'm quite excited about, because if you think about that, that's Montana, that's Nevada, that's a lot of places. So, other questions? Oh, Steve.
I'm just curious if you can share anything about river data. How's it going with Koocanusa? What's happening? It sounds like you've been at this for 4 years.
Yep.
What are you seeing in the waters in Montana? Can you share anything like that?
I'm not involved in that monitoring, okay. Steve. I think that Teck is very directly invested in reducing discharge into Lake Koocanusa, but you may be aware that the state of Montana is dropping standards, which is making it more difficult for them to comply. So they're chasing a target that's running away from them. I think that as these new SRFs are brought online, and there are multiple in the works, at that point, I think there will be a much reduced load. I think I don't want to comment on what fraction of load this represents, but yes, it will affect that and is intended to. Other questions? Kirk?
So if you were designing a new backfill, is it advantageous to, instead of doing end dumping where you get that segregation of size, to do direct placement where you have more uniform sizing through the entire column?
I think these systems, at least this one, has enough residence time that whatever those preferential pathways are, it doesn't really change the outcome, because the water's still in the reactor for a month or so. And if you're going to be able to saturate it and contain it in a pit, I think what you're suggesting is less important than if you were going to build a waste rock dump on flat and try to drive reduction in that dump. At that point, what you're suggesting is really important, because you're going to try to create these different zones that will support it. Yeah. But I think this is a problem, and we were talking about this last night, in terms of innovation. So I've had a number of people say, "Oh, Lisa, don't make a science project out of my permit. You know, we're just trying to get permitted here." Fair enough. It's expensive enough to go through permitting in a regulatory frame that can be uncertain. But these companies do need the bandwidth to innovate, and they need support to do that. And Teck, I think, is to be commended to the level of effort that they have put into creating sustainable and robust and resilient strategies. They could and did just go in and build a couple of active water treatment plants, but they had challenges there, and I won't get into that, but they considered this to be the superior technology. And so, yeah, I think we need to consider how we support innovation in mining. We don't have a Bureau of Mines anymore. As far as I can tell, EPA is not out there to help you innovate. How do we do that? So.
All right.
Happy to, we got one more in the back.
Yes.
You were talking about that it doesn't necessarily have to be saturated, and interested in looking at
There is research ongoing. I am permitted by tech to speak to what I've presented today. Yes, they are pursuing a lot of different options for accomplishing that. But I'm not able to speak to any of that specifically today. You bet. There you go. Oh, this too. Turn it off first.
All right, let's get right into the next talk. Resurrection of the Payne Mine by Emery Cup. Emery is a graduate of the Colorado School of Mines in mining engineering. He has worked in gold mining operations in Colorado and Nevada and coal mines in Montana. Emery is a mine manager at the Pan Mine located in Ely, Nevada.
All right, thanks. Morning, everybody. So I'll go through the resurrection of the Pan Mine. So I don't know if you guys know a lot of the history on Pan, but it was originally owned by Midway Gold, and they brought it into operation, ran into some issues with leach pad, went through bankruptcy, and then Fiore had picked it up. And then that's where we'll start our story. So the Pan Mine is over here in eastern Nevada. It's about 60 miles east or west of Ely. It was found from the Lyle Campbell Jasperoid back in 2013. That's where we found the outcrop of the gold-bearing material, and that's where we started looking. The gold is held in the Pilot Shale and Devil's Gate Limestone out at the Pan operation. The property is transected by the Branham Fault. It's a north-south trending structure that we find our ore in. We find it on the west side in the north and the east side in the south. We'll go through that a little bit here in the next slides. So in our south pit, this is where we ran into a lot of our issues. So that's where a lot of our clay-rich material is. Midway had put a lot of that material out on the pad, and it caused issues with percolation. Ended up making a nice pond that was elevated, and gold wasn't coming out. Here's a conceptual cross-section of our south pit. So we have quite a bit of the argillized material up here near the top of it, and then we do get to a silicified section in the middle, and then it goes back to argillized. Our north pit, this area wasn't originally supposed to be mined as much when they first went through the feasibility of Pan. But then after we had the issue on the leach pad, we realized we needed to get into that material so that we could make sure that we had adequate rock in our heap leach so that we could get that permeability. And the north area is primarily silicified material. We do run into some argillic areas in it, but primarily silicified. So what went wrong? So we stacked all this material out on our new heap leach pad, small junior company, can't really take that risk of anything going wrong. Put all this material out and nothing was coming out. We're just getting water ponding up on top and pretty much no gold coming out through the bottom. Originally, trying to bring some of that cash flow forward, we brought in a lot of our south material, which was that argillized material. It had a higher recovery by about 10% on a run-of-mine basis, and we were trying to just bring cash forward, and it ended up biting us. So from that, realizing that we couldn't just send all of our good material to the pad, we had to start bringing in the silicified from the north. That was about 50% recovery on a run-of-mine basis, and we started doing the blending out on the pad. We got better permeability for the leach pad, minimal ponding, and then working with SRK, we came up with our ratios of silicified versus argillic that we needed to send out to the pad. We primarily send a 60-40 blend of hard and soft, that silicified argillic material, and that allows us to keep our percolation. So when we first came in and started looking at some of the other things that we could do, we started overstacking our pad and then dozing it off to reduce the amount of compaction from the haul trucks on our cells. So we were pretty intensive on pushing all of our material with a dozer. It was kind of cost prohibitive, but it did get gold out the bottom. So we continued doing that up until summer of 2019. That summer we ended up, well, previous to that, we did 2 10,000-ton cells of crushed versus run-of-mine material and found that we saw a 10% increase in recovery from our silicified and about a 5% from our argillic. So we ended up going that route and sending that material out, and it justified crushing everything down to about a 6-inch minus, and we could put on cement and do kind of a conglomeration to help trap some of those fines. We don't overstack and cut material anymore, so now that we have identified that we can crush it at the crusher and get down deep enough with a deep shank ripper, we don't need to do that anymore. And then what we do is we, once a cell is stacked out, we've got an 8-foot shank on a D10 that we rip one direction and then come back with a 4-foot shank and then rip in our drippies. This is roughly what our operation is. We did add in a crusher that's not on this slide. It wasn't updated, but essentially coming from the pit, we do put on some lime at this point, about 3.5 to 4 pounds per ton. And then it goes through our crusher, and then the cyanide solution's added, goes down to the heap leach, and then we've got a train system full of carbon tanks and use absorption, desorption, and refining for that. Looking into our north pit, you can see back here, this kind of yellow section, that is the Branham Fault. So everything there on the left of that Branham Fault is pretty well our ore zone. If you're not familiar with the Carlin-style gold deposits, it's the invisible gold. So it's you can't find it by looking at it. You gotta test it with a chemical process. The material north has got a slower leaching and is very abrasive. It's expensive on our GET and drilling, but it does provide that coarse material for our leach pad. Looking in the south pit, it's a little bit harder to see the Branham Fault, but it's here in a sea of yellow. But this is soft. It drills very easy. With our DM45s, we'll exceed over 100 feet per hour on drilling, and that includes all the tram time. So it's very easy to drill for us. On the sampling end, this is another area that we'd hit once Fiore had taken over, is making sure that we're doing the right sampling and getting the right analysis on what we're actually mining. Because this is the beginning of everything for us, so making sure that we're not sending waste out to a heap leach pad when we're already trying to bring an operation back into the fold. So looking at our blast pattern, we do use contractors. Right now, Leadcore is our contractor for all of our drill, blast, and mining. And then here's a picture of our heap leaches. So in the back is the phase 1 pad that Midway had built, and that's where they ran into a lot of their issues. We came through and did kind of a cap and fluff by dumping, or we ran slots with the dozer and then dumped in rock material and then tried to mix it up with the dozer and Traco. And we're able to get that lower level broken up so that we could get that solution through and not be bulging out the sides of our pad. And then phase 2, we added this in around 2018, and we've tied both of these together, and we currently aren't dumping on them. I'll hit that here coming up. We rip in our drip tubes about 6 inches to a foot using a D6 dozer, and then that's how the cyanide solution comes through. Here's another picture. Our pad's pretty well windrowed once it's been put under leach. And then these are some of the new pictures of the ground is wet, which we're fine with it being wet, but there's no ponds. As far as dumping, before we started up our crusher, it was very difficult to make sure that we always had an adequate blend of hard and soft material at a 60-40 rate. One thing adding the crusher is it did give us that flexibility to crush the material and then come back and rehandle it and make sure that we're getting the right blends out there and we're not subject to operators just doing what they think is right. These guys are just moving dirt. They don't really seem to care half the time. This is looking at one of our dozers, deep ripping. So this is D10. It's got the shank buried all the way down, and they're pulling that 8-foot shank on this rip here. We are starting to look at whether or not we need to continue doing that 8-foot shank. We did some, I don't know what it's really called, but we called it the nuke test, seeing how far down we have that compaction from our 777s on it, and it's about 4 foot. So we are looking at how can we reduce some of our costs by not doing that deep ripping. North pit again, you see that Branham fault here in the middle in yellow. Everything to the left there is going to be our ore zone. We drill a 6 3/4 inch hole, and we're on 20-foot benches. Our haulage fleet is 777s and 992 loaders. We've got about 11 trucks out on site, and then we have a contracted availability that we have with Leadcore. So if we are down trucks due to maintenance, they do bring in additional ones to make up the slack if we think we're going to see an extended downtime. Here's our south pit. Just looking at as we've brought everything down. Oops. And then our barren pond here. This is where the solution goes back out, up onto the pad, and then down here. And then in the background is our preg pond where our pregnant solution comes off the pad. And then the refiner, or the ADR here in the middle. So we run up our barren solution comes across the pad and a 16-inch line, and then up the pad in 10-inch lines, and then we break them down to 4-inch and then to our drip tubes. And then one of the most important things is people. That we really stress that to the community and to our employees, that there's no ounce of gold, there's no ton of material being mined that's worth their safety. Always pushing that envelope on making sure that you call out something if you see it and it doesn't look right, and stop and work. We all want to get home, and we're all here together. It's kind of a recap. So we had the leach pad permeability where we had issues there. We took care of that. We had some grade reconciliation issues with the Midway model. We ended up doing about 45,000 feet of new drilling, updated our resource model. We brought an on-site lab so that we could do all of our blast hole samples in-house, and then got a couple more geologists tasked to site so that we can make sure that we're sending the correct material. We revised our ore stacking procedures, looked at our stability testing with SRK, and then moved into that crusher. This is a flight from 2020. So we have our phase 1 and phase 2 leach pads. I've got another slide I'll show where we have a phase 3 leach pad, which is about 2 million square feet that we're currently finishing up the overliner on. And then we've got our north pit where our more solidified material is. We have a layback here to the west that we'll be bringing on later this year, and then our south pit here at the south end of our property. We did just celebrate our 5th year anniversary. We had that in May. We had 5 years of good production, no LTIs, and that was a pretty big milestone for us, being a small company, getting that 1,000,000 hours. It took us 5 years to get there, and we were happy to get there with our employees and not getting anyone hurt. We're commissioning our phase 3 leach pad. We'll have that wrapped up hopefully here in the next month or so as far as the sign off to start putting the solution on. Since that 5 years, we've produced about 154,000 ounces and just shy of 50 million total tons mined. Continued to develop our reserves and resources out at Pan Mine. So we have our main pits here in the middle, and then all these red zones are areas that we're looking at for exploration. One thing that we have done as far as using a contract miner is that allows us to put some of that capital into drilling and not be tying it up with equipment. As mine manager, I'd prefer having everything in-house, but I'd rather see that mine life extend once we get that out far enough, then we can start looking at bringing things in-house. Production schedules, these are from 43-101s and tech reports that we've kicked off. So back in 2015, we were supposed to close our doors in 2018. 2017, we extended that out to 2023, and then we just released a tech report this January that takes us out to 2025. So continuing to see positive results with our drilling. We do release quite a few press releases on any intercepts that we get, and continue to keep people gainfully employed. And this is our phase 3 leach pad. It's pretty well all stacked with overliner at this point. We've stacked nearly this whole south end. A lot of the water drains. This is our high spot over here downhill. We did have some challenges with this leach pad. The underliner material that we needed to put down beneath our actual liner, we had issues sourcing good material in-house. So we did end up having to bring in some GCL, which is geosynthetic clay liner, in order to cover that up. And we were able to get pretty much everything stacked. I heard today that Leadcore has taken their crusher out, so they finished all their overliner crushing and will continue their placement, and then we'll be able to get it all under leach. I hurried this up a little bit to try and catch back up on times here. So, are there any questions?
What sort of reclamation bond do you have?
What's a reclamation bond?
Yeah, with the state.
So we've got our bondholders that we have it. I'm not 100% sure on that. I can get back to you as far as who our reclamation's through. But we do, when we update our CERC and everything, we go through our bonding as well.
What are your waste rock issues in terms of water quality? Do you have any, or what are the lithologies within the mine group that you're managing?
So our waste rock facilities are, out of all the operations I've been at around in Nevada, ours is very simple. Our groundwater is very deep, so we don't have issues with that. And then we have very low amounts of PAG material. And we ended up just dumping that in and encapsulating it. We don't really see anything with that. Anyone else? All right, thanks.
Thank you. Quick adjustment here. Sam Ash at the current time is not available online. Might be having some technical difficulties because he was on during the break. So we're going to jump to the next topic: design for closure, dry stack tailing facility conversions, and the impact on reclamation financial assurances by Tim Dreyer. Tim is out of Nevada. He's had 45 years of experience, 40 of which is in mining. And Tim, are you with us? I think that's a no. Dan, is he with us now?
Yeah, he was on. We just had his screen share.
Yes, I'm here. Just technical difficulties.
Not a problem, Tim. Glad you're here. Glad you're making the adjustment. Your slides are almost up.
I started them and now they're gone.
Well, that's not a good thing.
Hold on, just. Did you share your screen?
Don't worry, there's only about 85 people waiting for you.
Yeah, okay. I had it here and it went away. Let me get to there. Gonna go back in there.
But don't worry, I don't think they can throw things all the way to Nevada. They'll just throw it at me.
Yeah, that's good. That's a good thing. So now I should, where's my screen that I can actually share things? What happened to the Zoom screen? There it is. Can't get the Zoom screen back up. What the heck is it? Oh. I can
So
see.
maybe we're not at 3.0, we're at 2.8 trying to get there.
Where is the darn choice where I can you go out and come back? No, hold, stand by here. Just trying to get this back up. That Zoom screen isn't working for me. Can't see the selection for the. Let me see if it will work. For the share screen. Where is it?
You're on the screen here. You just have to put it on slideshow.
Pardon?
You're on the screen here. You just need to put it on slideshow.
Will I be able? Let's see.
I can tell you have a helper.
There. So
Okay,
you
good.
can see it and I can see it. Are we good?
I think so. Just hit slideshow and let's get the show moving.
Oh, there we go. So this goes to the other screen. Okay. We have screens that work in reverse direction. Okay.
You're done?
Pardon? I'm good.
Okay.
Thank you. Okay. Everyone hear me and can see the show?
I believe so. They just need it on slideshow.
I got it on slideshow. What the heck is going on here?
Go to this.
Where?
Oh, hold on.
Here's a slideshow. I've got it up.
Go to slideshow. Start from beginning.
It should be your bottom right icon. Oh, or right there is fine too.
Is it up and in slideshow? I'm looking at your screen and I can see it perfectly on mine, but I guess you can't see mine. Let's keep this again. I already went through a test on this and it didn't
Dan,
work.
can you direct them at all? Dan with Montana Pro will direct you through here.
So in PowerPoint on that slideshow, you just need to, on that top left there was a play slideshow from beginning button.
Yep, that's what I pressed.
I need you to press it. I watched you mouse over it. I didn't see it get clicked.
So is it up now?
So go to your screen, your
Yep,
laptop.
and then click that from beginning button. You were just moused over it.
It's not working. I'm clicking that button. Can you see me moving here?
2 screens with your computer set up right now.
Yes.
That I think is the issue. It's trying to put your presentation on your second screen instead of in Zoom. It might be easiest to just unplug one of those second screens.
Can you turn off one of these? Turn them off both. Wow.
Back on.
I don't think I'm in anymore on Zoom.
Okay. Yeah, there you go.
They're
We can see your PowerPoint is open. You're just not in the full screen mode. It's still like in the edit screen for us.
Can you see how to turn that other screen off?
This reminds me of a time when Brett Thiel handed me a tray of slides. They're all upside down.
Do you have anyone there who can help you change your screen share settings to the monitor in which you want to show us?
Let's see if I can do that. Where is that? Gifts. Oh.
Example. Back in the day, we used to have a phone at the desk because we didn't have cell phones, right? And so, in this particular.
It's second screen only.
That's what I did. There's where I am.
Okay, so you're showing.
Hey, we got it. Awesome. All right, we are ready to start when you are.
You can see it. I can't.
Double click that. Double do it.
Well, we can see it.
There. Now I can see it.
Perfect.
Thanks everybody for your patience. I spent the last hour testing this out until I got on Zoom. It didn't work. So again, my name is Tim Dyer. I'm here at Pumpkin Hollow in Yerington, Nevada. We have had this project for quite a while already. So what I'm going to talk about today is really a little overview of the project and why we call it One Project, Two Mines. And then what are we doing to really lead towards sustainable development at the end of mine life. Advance my slide now. Now it won't advance, huh? There it goes. So my I had a disclosure statement there, and somehow that disappeared. But I will be talking about resources and other aspects of the project. So offering the standard safe harbor statement that those are our best estimates. There it is. You don't have to read the whole thing. We'll just move through this very quickly. I've got this on auto, so I don't end up talking too much on each slide. So hopefully it will advance automatically. So here's my model of the life cycle of a mine, and the attributes of running a mine are, in addition to mining, you have obviously safety, community and stakeholders, environment, and in our case, in many cases, sustainable development. I've seen a couple of the papers, very interesting, on how we're attacking some of these legacy mine sites. Very encouraging and very interesting. We are a greenfields project, started with acquisition and exploration, and moving through that. So this is the life cycle for Pumpkin Hollow that started in 1960, and we went through a phase of advanced exploration, shaft sinking and drilling, and construction of our underground facility, and now we're mining and processing from that underground. But from the very beginning, we started with what are we going to do to transition into a post-mining sustainable land use, and that's driven a lot of what I'm going to talk about today, some of the platform that we set up to hopefully make that happen. So I'm just wondering if this, I thought this was on. So a little history. It was discovered in 1960s by U.S. Steel looking for an iron deposit to support their Utah steel plant. And then a number of other companies, I'm not going to read every line, went through here and looked at the property. Step to developing the property until Nevada Copper acquired it in 2006. And since then, we've been doing drilling, development, and of course, the big deal was this land. Talk more about it as we go forward. One of the aspects of Pumpkin Hollow is what I call real estate, location, location, location. Nevada is the #1 ranked jurisdiction in the world. Now, of course, Idaho and Montana and some of those are not too bad either. But we are 100% on private land. We're in a desert climate. The local topography is optimal for efficient environmental management. And here's the key: 5 inches of precipitation, 5 feet of evaporation has really enhanced our ability to manage water at the site. And it's facilitated our ability to do a dry stack method, which I will talk about. We also have very little environmental values, no sage grouse, no endangered species, no cultural resources. So as I often say, we're a charmed location. We started advanced exploration in 2012. That's our head frame for our main shaft. We privatized the land in 2015 with the direct purchase of land from the federal government, which was managed by the BLM. By the way, very, very best experience I ever. The BLM, they did it in about 9 months. It was amazing. So we completed the main shaft, and we've got a vent shaft that's completed and operating, and you can see all the other facilities. We want to go to a 6,500 ton a day underground mine, which would be the largest underground mine in Nevada right now. So, and again, we're looking at dry stacks tailings. Here's a little bit about where we are. In Yerington, this is the old Anaconda Pit, another Atlantic Richfield BP site. They're starting reclamation on this site. We have our east underground deposit. And a couple miles to the west, we have our open pit deposits. We're developing the underground, have a feasibility in the open pit, and all of these are permitted. We also have these exploration areas out to the east. Here's a kind of a site layout with everything in place. Here's the footprint of the underground where we're currently operating, and our dry stack tailings storage is here. And then we acquired the existing mineral patents were 1,500 acres of private land, and we endeavored and successfully completed the land transfer to privatize everything around that. So I'm just hoping the screen, I guess this may not go forward. So here's the boundary. This orange and black line is the land conveyance boundary, and included the tail of the dog to the power line. This is the main NV Energy power line. 10,000 acres was acquired in that transfer, and this shows kind of overlays ultimate development of the project on top of this land area. The white was patented mining claims, yellow was land transfer. Some of these are different area. This is a conservation area we worked out with local residents. The city of Yerington retained 900 acres up here. So we're in a very good position with over 10,000 acres of private land to facilitate our future mine development. And I'll show you on the next slide a little bit about how we set this up. But this was done via the National Defense Authorization Act of 2015 for fiscal year 2015. It was passed in December of 14. We were one page in that multi-thousand page legislation, section 3009A. 7 other land conveyances in Nevada were in that bill. No other privatizations have occurred since this bill was passed. Subsequent to that, the city of Yerington transferred the majority of land to us. They retained this. God, I put this too fast. I'm going to go back. Sorry. Previous. Because this is an important point. Let's go previous. Sorry about that. So we've zoned this all. We created a special zoning district for mining and processing and solar development and everything. So really, we have a platform where we're annexed into the city of Yerington. We're zoned for mining. So we're really in a good position. This is part of something I'm really not going to get into, but this is a partnership with the city. The land conveyance occurred because the city wanted it. They wanted us to get net proceeds of mine share. Absent annexing into the city, they would not have received net proceeds of minerals taxes or property taxes. So now as a key stakeholder, the city's a key partner for us. They're going to be benefited by this land transfer. Here's a little bit, I'll go very quickly on the underground site. This is our current site. We're looking to the kind of the southwest here. This is our land area out here. You can see our east main shaft, our east north ventilation shaft, the hoist house, where we run. We have a conventional copper flotation processing plant, a filter plant for trade. And here's the cell one of the initial tailings cell over here that's unlined. So right now we're in ramp up. This project is just starting up right now, and we full production here within 3 to 6 months. Once we get, the COVID has really set us back, so we're trying to make up for that. Here's a quick isometric view of the deposits for the underground. We have the east north underground, the east south, the main shaft, the vent shaft. We also have this deposit that in the future we'll access, and we'll go through this zone, which has got inferred resources that we decided to wait till we get under, actually develop it, because we had enough ore, the red and green, to develop. This is the configuration. Pretty much right now, it's actually more than this on a daily basis. You can see the major facilities, and you can see the mining areas, the east-south stopes and the east-north mining stopes, and we're moving toward the east-north right now, and there's the bottom of the shaft with the dump pocket. Metric of the open pit project, it's right now we've done feasibility and permitting. It's fully permitted. It's got 2 pits and 4 billion pounds of copper. You can see some of the things. And here again, looking at the open pit and the underground, we also have this ground that we're going to start drilling on, and it looks very promising in terms of development. So beyond, what can we say? Well, you can see the site doesn't have a lot of high resource values. There's no wilderness, no endangered species, anything like that. The existing Yerington community really grew up with the Anaconda mine, and most of the people that were here then are very anxious, very supportive. We've got pretty good infrastructure and a pretty good labor pool, although all of the West are finding difficulties filling positions in mining. But it's a desirable place to live. And we've got partnerships with Western Nevada College, University of Nevada, Reno, to also help people aspect of our business. So what our copper flotations are very amenable to filtration, which led us to say, could we do dry stack tailings? We did lots of tests. Tailings filtered to an unsaturated taste, less than 15% gravimetric moisture. So what does that mean? We decide to dry stack. It means we can reduce the land disturbance, eliminate a dam in a high seismic area, lining a large tailings facility in Nevada with a high saturated, put a liner in. And here are all the other attributes of a dry stack tailings. It costs more operationally, but on the long term, it's also the way to go in terms of, for these reasons. We remove the interstitial fluids so we don't have to manage those forever. We reduce the size of drain down ponds during operations at post-closure. We can do concurrent reclamation on these cells as we complete them. And we're using some of the tailings for underground paste backfill. So a lot of these attributes really helped support our decision to go to dry stack. And really quickly, this table shows us that we can get at least a 28% and more than 50 to 65% water savings. 3 main issues in Yerington: water, water, and water. It's an over-allocated basin. To find a way to use. Here's some of the modeling that we did that demonstrated that unsaturated tailings are driven by matrix potentials and not hydraulic gravity flow through the system. So what are the differences? Saturated flow is governed by Darcy's law. The hydrologist, I understand a little bit of it, but I know just from what we're observing that we're in an unsaturated system. It's driven by matrix potential, and it's your content of the tails. And here's another graph that shows how the conductivity of these pores are when they're unsaturated, and it really drops. This is the model that Tetra Tech did to seek permission to do dry stack, and it just shows the theoretical moisture contents in an unsaturated tailings. The blue areas are drier than the red. The highest moistures we anticipated were 0.18 or 18% moisture. So these I believe are very stylistic. When we actually observe this thing, we're going to see, number one, lower moistures. I absolutely believe that. And we're going to see no seepage into the ground. So this is a photo of our DryStack test cell. The state's permission to construct this without a liner, so we could demonstrate that the dry stacking into groundwater. That is the number one issue at the old Anaconda site, the seepage from the tailings. And here are the monitoring systems we have in place to test the moisture, like lysimeters that are connected to data collection. And we're going to be doing that for quite a while now in terms of really measuring how these tailings are going to perform. So again, DryStack, we believe, is a very beneficial thing for long-term. You know, one of the huge benefits is it reduces our reclamation bond because we don't have to bond for managing water. So we start with the future in mind. Again, we're zoned for mining, industrial, commercial development. We have excess land. We expect to have mine suppliers coming out and setting up shop here. We have electric power, municipal water agreement with the city. We'll probably do a water line or a water treatment plant, and we'll probably do a future wastewater treatment plant. So what is possible out here? Electric power, we have the infrastructure in place on site. NV Energy is installing their GreenLink right next to us. Solar potential is 200 megawatts. Geothermal is still not well understood, but we got 100-degree water at 1,000 feet. And my vision is that we have possibilities for pump back and other energy storage. So that was very fast. I'm sorry, I wanted to go through it quickly, but this is our vision for our project, is to have a safe and healthy at work and in our community. And that's consistent in the mining industry. We are working very hard to support local hiring and training and education. We want to be the employer of choice. When we get open pit going, we'll be the largest taxpayer and the largest employer in Lyon County. And here are some of the other attributes of our community relations strategy. So that was very quick. I'm sorry, I thought I was going to be too long, but I'll entertain any questions now.
Tim, thank you very much. And do we have any questions? Yeah, all right, Warren.
Can you say anything about geology and ore grade?
Yeah, I can. So we have, like I said, the two different deposits are different. The open pit is a large, kind of lower grade, more consistent, but they're both skarn type deposits, so they're discontinuous compared to a standard sulfide porphyry system. Thank you, Michael. So we're on the east side of the valley, and it's a skarn. Underground, we have up to 6% copper grades, but it varies. We expect to have an average grade of 1.5%, and that's an iron oxide copper gold system. So we do get gold and silver that floats with the copper. So it's let's say geologically and hydrogeologically very interesting. You can go 20 feet, and the hydrology and the geology is very different. So again, from a mine planning view, it takes a little bit more than just going into a porphyry system that's pretty consistent and pretty homogeneous.
Do we have any other questions? We do. A gentleman's coming up.
Hello, I was wondering how high are you stacking the tailings, and did you see any limitations in how high you could stack them?
Nick, how high are we going? Nick Atimo, our environmental manager, is here to answer questions, but how high are we ultimately going on that dry stack?
So for cell one, we are permitted to go up to 75 feet. For the test cell, we are permitted to go up to 30 feet. And the stack height for each bench is about maximum of 5 feet.
And then ultimately we'll go higher than that.
Oh, yes, ultimately we will.
On the ultimate dry stack, I think it was it 300 or 600 feet? Those numbers escape me right now.
That's 300.
300 feet. So it's, you know, and I didn't point out when I was going so fast that one of the benefits of the dry stack is that our land footprint is significantly smaller. And, you know, it just reduces the amount of growth medium we have to salvage and the amount of growth medium we have to put back on. So again, that helped reduce our bond significantly. So our bond is much lower than the typical mining project with a tailings dam.
Okay, so you didn't have any like stability issues there for that maximum height for the final design for the mine?
No. We've done a couple of stability studies and showed, as you saw in the picture, it's a magnetite hosted ore body right now. There are other skarn type minerals there, but right now that black tailings is basically dominated by magnetite. Honestly, it's pretty heavy and it's probably less prone to dust and everything, but it's very stable. We've done setbacks on the lifts. So all the stability analysis we did showed that it was not going to be a problem. And we're observing that in the field right now. It's very competent material.
Thank you.
Any other questions? Lisa Kirk.
So I would imagine that the modeling that's been done takes into account the very dry climate conditions and the great depth to groundwater associated with your site. In the past, I've worked at a site in Chile where dry stack was used in the periphery of the Atacama Desert, where things are arguably as dry as they get, or pretty close to it. And what they found was that as the material consolidated, that less than 15% or whatever your cutoff number was for moisture content actually was released as a result of consolidation. So my question is, have you done any geotechnical work to evaluate that potential?
A little bit, but again, we haven't really predicted. You're saying that by consolidation, by consolidation, you went from 15% gravimetric to maybe a more saturated condition. Is that correct?
And water flowed from the facility. I don't remember the exact numbers, but 15% may not seem like a lot of water, but if it's quite metal rich and or acidic or has cyanide, and what we did observe was that it moved. In that case, it transported mercury with it, and so it's quite a management problem in groundwater as a result.
Yeah, you know, that legitimate concern, and certainly we did a lot of hard looking at that type of thing. Number one, we don't have cyanide. We don't have any kind of inorganics, you know, that are deleterious to perhaps groundwater. There's elevated arsenic in the entire valley, and that was an issue at the old Anaconda site. But we believe that we're managing it. But part of our commitment is to monitor this, certainly during the early phases. So if we see any kind of issues like that, we can deal with it. The other thing I'll point out is that we didn't know for sure with lab tests what the permeability of our tailings would be. But since we've actually been making tailings, I'll let Nick tell you what we've shown the permeability of a compacted tailings bases on the dry stack.
Yeah, so preliminary tests that were carried by Geologic, which is our engineer of record, shows that you know, we can have as close to as 1 × 10⁻⁻⁶ for permeability. Our moisture content that we are seeing or we are permitted to is between 11 and 15%, and the plant has been able to maintain that moisture content, which is a very good advantage for us.
Yeah, so we are well generally under the 15%. You know, I dealt with a filtered tailings in China once, and one of the problems was that they couldn't. It was a gold operation, so it was very difficult to filter, and so they got they got much high saturated material put out on their tailings. Now, one of the advantages of Pumpkin Hollow, because it's iron oxide, copper, gold, magnetite hosted, we're at 100 to 150 microns, which is all the tests we've done, everybody says we just can't believe that you can get the water out of it like you do. But multiple tests have demonstrated that, and the mill really, it's not having a problem extracting that moisture. Of course, we're going through startup and trying to get the filter plant going. Not a lot of people are filtering that much material, so we're kind of pioneering in that end in terms of getting a filter plant to run efficiently.
Thank you.
Did you hear that question?
No, I didn't. Could you repeat that, please?
I certainly can. How do you control from washouts and storms? What controls are in place?
I'll let Nick answer that question.
No, so we have setbacks on each of these parts. So we have the test part, and then we have one we call cell one. Cell one is a line facility that has a channel covering a certain percentage of the pad, the perimeter of the pad. So the channel is basically one of the controls for storm water, if in case we have any major storms. And the good thing is that, as Tim did in his presentation, the yearly precipitation in this area is only 5 inches, and we have a lot of evaporation taking place. So even if we have any major upset in precipitation, evaporation helps us a lot in controlling those things.
Yeah, as Nick points out, we do have siege ponds below the dry stack. So any kind of runoff that comes off of and it's all contained, mine effective water is contained on the entire site and goes into lined facilities. So again, our normal storm water is very minimal.
Yep.
Of course, over a period of mine life, 30 years, we can expect to probably get some big storms, but we believe that we have the containment to deal with that. And so, yeah, it's managing stormwater at Pumpkin Hollow is not our biggest challenge with 5 inches of rain. I've been here for 14 years, and I've seen maybe 2 storms that we actually had runoff, significant runoff that lasted like, maybe an hour. Little washes that we have will have water run in them for an hour or 2. So we do get water. You got to be prepared for it, but it's not a typical problem as I experienced when I worked in Arizona, where we had 6 or 7 people dealing with stormwater management all the time because of the amount of precipitation we got there in the bigger storms.
Can you talk about the size of your reclamation bond and what form it takes?
Yeah, well, what is it, about 7 million?
About
now?
7 million.
For the underground, we're at about 7 million. Of course, when we get to the open pit, we're going to have a large mine rock facility, and that I think our projected peak bond will be about 20 million. But part of the reason for that is that we're going to be able to get bond reductions annually as we do concurrent reclamation. And then again, you look at some of the bonds that some of the tailings operations in Nevada are paying for long-term residual solution management. It's significant, and you start with day one. And if you have a mine life of 30 years, you've got to post that bond for 30 years. So we have zero. The other thing, again, I went through our vision to convert things at site. So in our bond, we've actually identified facilities that have a post-mining land use, and the state has accepted us as long as you identify a reasonably and defendable post-mining land use for electric power, wastewater treatment, water, buildings, all of that stuff. Because we're on private land, we don't have to demolish anything. We're gonna spend the next 20 years trying to figure out how to make that work for sustainable post-mining development. So I'll give you an example. Anaconda shut down here in 1978. What I say is that typically they turn the lights off and everything stayed. That was like suspended animation for 30 years because nothing happened at that site. Now, very fortunately, Field stood up and said they're going to do the entire remediation on the site, which is a good thing. That your conference understands that some of those legacy sites take 10 or 20 years to get agreements with the federal and state governments to allow their cleanup. That doesn't become a endless cost for everybody. So again, we think we can convert up a lot of our facilities, and we think we can develop other industrial and commercial uses concurrent with mine development on excess lands. So that's going to help transition us for the future. And you know, I've been at this business for years, and the biggest drawback to post-mining land use is you wait till the end of the mine life, and I say it's too late. You haven't thought about what you have to have in place to be able to do a post-mining land use. So I worked on Island Copper, and they had some great ideas, but it was at the end of my life, it was too late. They needed 10 years to get that to work. And so start with the end in mind. And that would be a mantra for every mining operation. Now, we're fortunate because we're 8 miles from the center of Yerington. So in terms of not being 50 or 60 miles from any kind of, you know, settlement, or I mean, you know, a city or something like that, we're in a very favorable situation. We got rail, we got highways, we got all of that. So we're going to be in a position that I think we can do that. So part of that was inspired in my career by the company I work for, Asamara Minerals, bought 100,000 acres out by east of Reno, and it's now the largest industrial park in the world, Tahoe Regional Industrial Center. And the day we closed on that, I told my boss, I said, if we don't find a mine here, somebody's gonna make this a big deal. 100,000 acres of private land is significant. So now Tesla, Switch, and Zulily, and all of them are out there at the Tahoe Regional Industrial Center. They're almost built out now. So they're looking for large pieces of land for more. So hopefully those opportunities come to us.
All right, Tim, and one last question. It came from a virtual viewer. What does the cap reclamation look like for the FTDS?
Repeat that, please. For the dry stack tailings?
Yeah, what does the cap reclamation look like for the FTDS?
I don't remember we are going to put a cover on growth medium cover on the tailings facility. And it's pretty minimal because it doesn't have to be at ET cover necessarily. We did a demonstration that got us down to a foot of cover for the
between
final.
6 and 12 inches.
12 inches. So yeah, we did quite a bit of study, approached the state and said, we don't need 3 feet of cover to prevent infiltration of water. Again, because we're in this very dry environment, that's not necessary. Where you look at Barrick out at Elko, they're putting 3 to 5 feet on top of their waste dumps. So just because they have so much more snow melt and precipitation and that type of thing there. So I don't know what, our total bond is just under 8 million. So probably covering the tailings right now is a couple million, maybe?
A small percentage of it.
Yeah.
All right. Well, thank you very much, Tim.
Well, thank you. I'm sorry. I really was looking forward to getting there, but we're in the middle of ramp up right now, and I just couldn't be in 2 places at once. I did listen to some of the papers, and I found them very interesting, and I'm sorry I missed the conference.
Well, and thank you for your flexibility for jumping in front of Sam, because we have now Sam online and he's ready to come on. So thank you, Tim.
Okay. Thank you very much.
And we'll be moving back into the next topic, happenings at the Bunker Hill Mine with Sam Ash. Sam, are you with us?
I am, and apologies, I got my time zones wrong. I really appreciate Tim jumping in there and saving me.
Not a problem. Well, Sam, I'll let you start off, and
you want to watch this?
Looking forward to your talk.
I have to listen to him.
All right, thanks a lot. We'll get started. Just want to check and make sure that everybody can see my screen now.
Hello?
It says screen sharing, but it's not on the screen.
Okay, let me stop and, okay. All right, I'm not sure what has happened here.
Do you have double screens?
Yeah, I do. Maybe let me take that out. Maybe that'll help.
Yes, please.
All right.
Well, we see you.
Okay, that's an improvement. Let me try sharing my screen one more time here. I think everything just for some reason stopped working. How's that? Am I sharing
Here
now?
we go. Now we're talking. Thanks.
All right. All right. Very good. And I have control now. So great. So again, apologies for causing us to go out of order. That was completely my fault. I completely forgot that I'm in the Pacific time zone, even though I'm just over here in Kellogg, Idaho. But anyway, we'll get going. It's really my pleasure to be talking to you today from Kellogg, Idaho. We're in the midst of really bringing an iconic U.S. silver mine back to life here at Bunker Hill. You know, I think that the Bunker Hill presents a really kind of unique opportunity, and one that the executive and management team at Bunker Hill feel time has come. You know, I think that all around the Western United States, there is a tremendous mineral endowment that is underutilized because it's distressed for a variety of reasons, most typically environmental or social mismanagement in its past. And I think that, and we think that really the time has come to put those mineral endowments back to work in a very different way. You know, there's a bright future for those mining sites, and a bright future for economic development all through the Western United States in rural areas, but done in a very environmentally sustainable and responsible manner that actually atones for and corrects a lot of the mistakes that have been made in the past in mining. And really, that's really one of the key reasons that brought us to the Bunker Hill mine is the opportunity to come into a site that was absolutely had a sorted environmental track record, and show that with the right focus and the right approach, that a very different outcome environmentally and also socially for the local communities is possible. So we do have a entirely new leadership team. You know, myself, I came from Barrick. I actually know Nick Atiemo quite well from my days there. And I'm joined with my executive chairman, Richard Williams, who is the chief operating officer of Barrick, and Brad Barnett, who headed Barrick's global closure portfolio. And interestingly enough, you know, that put him at the forefront of some pretty interesting discussions with Superfund sites in Barrick's portfolio. So really, Brad has been a great help to the team and really driving forward with some of the challenges that we have here at Bunker Hill. Bunker Hill, it is a world-class mineral endowment. There's no doubt about that. And we have a vision that goes well beyond Bunker Hill. And that vision really is to demonstrate that the tremendous mineral endowment that exists through the Western United States that is distressed for environmental reasons can really be approached in a different way through collaboration with local communities, through collaboration with regulators, and brought back to life in a very sustainable and positive manner. Our strategy here at Bunker Hill is really quite simple. We have a robust plan for a rapid return to cash flow, and then over time realizing the upside silver exploration potential that exists here at the site. You know, we see this as a deposit that has a mineral endowment that will support, you know, a multi-generational operation that will be at the forefront of environmental and social performance, and key to the
development of the local area as well. So the Bunker Hill Mine, located in the Silver Valley, we're on the western, we're on the western extent of the Silver Valley here in Kellogg, Idaho. Hecla runs the Lucky Friday complex on the eastern extent. America's Gold and Silver operates the Core Galena complex. And we're really quite excited about Bunker Hill. There's a few things that are somewhat unique that people might find interesting. Bunker Hill produced 165 million ounces of silver over a 100-year operating life. And really, there's still an extremely large unexplored potential around Bunker Hill. The Bunker Hill, the deepest level is around 4,000 feet, which makes it about half as deep as the Lucky Friday mine, and a little over a third as deep as the Core Galena complex. So what you're talking about is there's enormous down dip exploration potential, also along strike, which is really quite exciting to us. But now I just want to run through a little bit of that history that I was talking about. So the Bunker Hill mine was started in the late 1800s. And over that time, it produced over 5 million tons of base metals from around 35 million tons of ore extraction. Primarily lead and zinc. There was a lead smelter and electrolytic zinc plant. Silver was mined primarily as a byproduct of lead production. And over that 100-year operating life, there was very little to no environmental regulation. This second picture here, you can see what the local environment looked like kind of at the time of closure. No trees, a completely denuded environment. There is no doubt it was an environmental wasteland that was created by the operation of the Bunker Hill mine and smelting operations. So 1981, the mine was shut down as a result of the Superfund Act, the Clean Air Act, the Clean Water Act. And the EPA has done a fantastic job initiating cleanup over the last 40 years. You fast forward to 2017, and there was a consent decree reached that clearly articulated all historic environmental liability associated with the Bunker Hill site. That set that at $20 million. $1 million has been repaid, and we're in the process of discussing with the EPA how that remaining liability can be structured and met out of cash flow on restart. Fast forward just over a year ago, the current executive and management team joined what was essentially a dormant company. We raised a little bit of money, and we focused on really three key areas: the technical aspects, advancing the project technically. We did 3 drill campaigns, published 2 43-101 compliant resources, and a PEA that articulates a pathway towards restart. That was key. That was the first real technical work that had been done in 40 years at Bunker Hill. We also focused on the key environmental challenge, which is water quality. We have weekly discussions with the EPA about how we can move to a point where the responsibility for water treatment comes back into the purview of the mine and the mining operation. Right now, all of the water that leaves the mine reports to the EPA-owned and operated water treatment plant, where it's treated to discharge quality and then discharged into the Coeur d'Alene River. And then we also focused on quite a few corporate governance items that, as you can imagine, in a dormant company, needed some attention. So it's been a busy year, and really, just to give you an idea of some of the project economics and why we're excited about this project, it has a very strong NPV, short payback, well positioned in the bottom third of the cost curve, a 10-year mine life. But again, that's based on the current resource, which reflects the historic SEC compliant reserve. So really not a whole lot of exploration has been done yet, and we certainly see this as a multi-generational asset. And then there's huge upside potential through exploration on the land package, down dip expansion, and also along strike. And really that no surface tailings, this is where we'll start to get into some of the aspects that are more pertinent for this forum and this discussion. We're not going to have any surface tails deposition. We're not going to have a surface processing plant. We're going to place our processing plant in the underground mine, and we're going to do underground tails deposition through a combination of geotechnical paste fill and filling historic mining voids and stopes in the underground environment. We're lucky to be the recipient of a mine that is in really relatively good condition for being over 100 years old and had 35 million tons of ore extracted from it. So there's a large amount of openings and voids that are accessible for tails deposition. And really, that's a key component that is going to also allow us to address the key environmental challenge, which is acid mine drainage in the mine. The mine right now discharges between 12 and 1,500 gallons a minute at a pH of around 3, and with a high metal loading, primarily zinc in that water, which is again treated at the EPA water treatment facility. Now, when we look at that water stream and we follow it upstream, I'll just skip forward here a little bit. This is probably an appropriate diagram to look at. What's interesting is, where does that water come from? So most of the water is surface runoff and surface inclusion through Milo Creek, through Deadwood Creek, and through an area called the Guy Cave. The Guy Cave was actually a block caving operation that was initiated in the late 50s. And through all of those areas, surface runoff and drainage seeps into the mine and through high pyritic zones, creating the majority of the acid mine drainage problem. When you follow that 1,500 gallons a minute back into the mine, and then you follow all the individual water streams and you do the water testing and understand where the genesis point for this environmental problem comes from, you quite quickly realize and come to the conclusion, which we have, and we've proven this, is that 90% of that problem comes out of a highly acidic water stream between 6 and 20 gallons a minute, depending on the time of year. And that's really associated with this area you can see on the diagram called the Guy Cave, where you have highly acidic, high pyrite content, highly fractured rock where that chemical reaction is taking place. So we already have separated and worked on facilitating water flow through the mine. Again, it's a chemical reaction, so it's all about time, oxygen, and flow. And then, of course, contact with a high sulfide environment. So just by putting in and separating that water stream and putting that water stream into a scoping test water treatment process underground, we were able to reduce the metal loading coming out of the mine, out of the Kellogg Tunnel, by 70%. So there's some really interesting, low-cost, high-impact solutions that we're looking to do as we move forward and look to reduce the intensity of ongoing water treatment that's required in the mining operation. So in the short term, water treatment, we're weighing the options of whether or not we continue to pay for and use the EPA water treatment facility, or whether we look at instituting a longer-term water treatment solution internal to the mine. There's a lot at the moment. We're working with a group called Mine Water out of Colorado. They've effectively treated treated water at contaminated sites, the Gold King, Captain Jack, both of which were Superfund sites, both of which have similar flows and similar water qualities to what we're looking at. And there's really some really interesting emerging chemical processes, potentially using the mine pool as a bioreactor in that process, which is really interesting. The technical work is ongoing with that, and we expect to have some of those results coming out later in the year to confirm just some of the baseline chemistry. But what's really interesting, when we look at Bunker Hill, certainly the mine is important. I'm a mining engineer. I come from a mining background, and really the mine is kind of the nucleus of the opportunity here. But when you look at the Silver Valley and the area around Kellogg, what you quickly realize is that there's an opportunity to incorporate, along with mining and the and water treatment and the management of acid mine drainage, redevelopment and reuse of the water and the water activity, carbon offsets with the intense forestry opportunities that exist. And we're really looking at this as a system and a opportunity to kind of fundamentally show what can be done and showcase what can be done around a historic mining operation that is distressed for environmental reasons. We're fully aware that on the mountain that the mine is underneath, there is an operating ski resort. Our vision is to operate a successful mining operation in such a way that the local community, unless they are coming to work here, really doesn't see or notice any impact. And that's really exciting. And I think for myself, that's what excites me about being a part of this company and really moving it forward, is the opportunity to show that mining can operate in an entirely different way as we move forward. So what are the next steps? What are we working on now? We're in the middle of a restart financing process. We're in engagement with the EPA around restructuring the meeting the commitment for 19 million in historic water treatment payments. We're looking to purchase the mine. At the moment, we don't actually own the mine. We have a lease with an option to purchase. And then we're working in the financing side around upgrading some of our listings and where we're going structurally as a company. On the operational side, we have a geophysics program going, looking at exploration opportunities on the larger land package out of the existing mine footprint. We're continuing to digitize and make use of all of the historic geologic and technical information that was available to us here at the site. Over 100 years worth of data. It's really pretty interesting. We're also going through the technical steps to de-risk and make ourselves restart ready. Mine plan optimization, geotechnical studies, rheology to better understand the paste fill for geotechnical reasons, but also the tails deposition, OpEx, CapEx optimization. We're looking to be a fully electrified mine without any diesel mining equipment. And we're looking at some toll milling opportunities as we to bridge the gap into pre-production. And again, one of the key differentiators and kind of unique things that we're doing here at Bunker Hill is that we're not going to have any additional surface disturbance. The processing plant will be located in the underground environment, reusing some of the existing underground infrastructure that's in place. And we won't have any surface tails facility. And in conjunction with that, over time, that acid mine drainage challenge that we face now will really, we believe, we have a realistic and real shot at turning it completely passive in nature and reducing the impact and actually providing a source of water for further development opportunities in the area surrounding Kellogg and really help the revitalization effort around Kellogg. Kellogg was a mining town. When the mine went into closure, it really has struggled economically and socially for the last 40 years. And we're excited to be a part of that turnaround process. So I think with that, I'd be more than willing to answer any questions.
Thank you, Sam. Any questions?
Say anything about the geology of it? Sam, can you tell us, give us a summary of the geology of the historic mine?
Yeah, absolutely. So, and actually I'll share my screen again and maybe it'll help with a slide if we come back. Yeah, this one probably works. So the geology is essentially it's a deposition. There was two depositional events. The first was a zinc dominant depositional event. The second was a silver enriched galena depositional event. The deposition occurred in a overturned anticline in the harder quartzite units. So as that anticline formed, the fractures provided a conduit for fluid movement in the harder quartzites, and that's where the stronger depositional events are located. Where the two mineralizing events intersect, you get hybridization and enrichment, siderite replacement and enrichment across all three primary metals, lead, zinc, and silver. Those hybrid ore zones were some of the the richest ore zones in the mine's history. So for people who know a little bit about the Bunker Hill mine, the March ore body was mined for over 50 years and over 20 million, or well, over 10 million tons of ore extracted out of it. And then as you get deeper into the mine, you see the some of the lead, galena, silver mineralization begin to change in nature a little bit. And we believe that it's beginning to near the point where it's going through a zonation change, where rather than lead being the dominant mineral of deposition, you'll begin to see silver become more dominant in the more dominant metal in deposition. And that's kind of characterized as the lead-silver ratios begin to approach 1-to-1. And there's indications, particularly in the J vein, the Mac, the Francis, the Emery, and the Ike, which are shown on this map, that that may be occurring. We may be reaching that point. Bunker Hill is relatively shallow. It's only about 4,000 feet deep on its deepest level. So we have a lot of room to grow in that down dip expansion.
Thank you. I know that in the late stages of operation of the earlier mine, that there were a lot of really spectacular secondary minerals produced. You're going to stay in the specimen business too?
Yeah. It's interesting. Bunker Hill is for a long time was the only known source of pyromorphite in the world. Now I think that there's been some additional deposits found over in China, if I'm not mistaken. But certainly Bunker Hill is famous in the mineral specimen collecting world for its pyromorphite. Right now, I can't say that that's in our plans, but certainly, as we look around and if we come across specimen quality minerals, we certainly wouldn't be looking to just grind them up and process them. We'll be looking to set them aside.
I'm sure a lot of mineral collectors would like to buy American.
I would hope so.
All right, Sam. Well, thank you very much, and thank you for attending the conference virtually.
Thank you all so much for having me, and again, apologies for the mix-up on time zones there.
Well, a little virtual growth rate we've just had today, so we're in good shape.
Thank you.
It's going to be a duel with both Lacey and Aaron. Lacey Morrison grew up in White Sulphur Springs, where the Black Butte Copper Project is located. She has received a BS in environmental science, with a major in geology from the University of Montana Western. She's been working with Sandfire Resources America since 2017, where she oversees drill programs, logistics, operations, and reclamation. And she will be joined with by Aaron Bennett as a project mining engineer at the Black Butte Copper Project. She received a bachelor's degree at mining engineering from Colorado School of Mines and conducted a postgraduate study in geology at the University of Northern Colorado. Over the past 6 years, Aaron has worked on various projects to optimize operations efficiency in underground hard rock metal mines. And our talk today is Black Butte Copper Status Report. All right.
Just waiting on a presentation. Okay, perfect. Thanks for that introduction. Again, my name is Erin Bennett, and with me is Lacey Morrison. She's one of our project geologists. And today we're just going to give a brief overview on the Black Butte Copper Project and touch on a little bit of the status of where we're at today. Oh, that's laser pointer. So just a quick disclaimer, even though we have gone through phase 1 construction and we do have our mine operating permit, we are still a development company. So we're legally required to put this disclaimer up. And this presentation is a forward-looking presentation. So to touch a little bit on the project timeline, so the Johnny Lee deposit, which is currently permitted, was actually discovered in 1985, but the companies who did first drill out those holes were looking for zinc. They were not interested in copper, so they kind of put the project to sleep. Fast forward to 2009, one of our current vice president of exploration, Jerry Zig, was approached by private landowners, and they kind of wanted him to revive the project. So he was working in Alaska at the time, and his company created an offshoot, called it Tintina Resources, and they kind of brought the Black Butte Copper Project back to life. So in 2015, the draft mine operating permit was presented. And fast forward to 2020, in April, we actually received a record of decision to go ahead and be able to mine. And December of 2020, we published our feasibility study. And another kind of cool tidbit, a couple weeks ago too, we actually completed a purchase of a little bit under 535 acres. So we actually do own the surface rights of our mining project. So that's kind of cool there. So this is just a little illustration here. So on the left side there is how our project looked before phase 1 construction. And on the right side is how it currently looks after phase 1 construction. So during phase 1, we were able to put in a brine and contact water pond, which you see over here on the right. And also just off to the screen is our portal pad. So we have a good start on our project, and now we are just moving forward. Just wanted to touch a little bit on our sustainability model and our mission statement. As you can see, people and values are our foundation, and we kind of just wrap our whole company around that motto. We also are in our pillars. We have environment, resource, and stakeholders. So really, we build our whole project on that. If we can capitalize on those, we can bring our project into the technical and commercial sphere, and then add value and grow our project. So touching again on our people, so our team is our #1 resource. We do believe that each and every person that works for Black Butte Copper brings value to the company. We're all Montana-based, and we live and work near or in White Sulphur Springs itself. We now have 22 full-time employees, so relatively small still, but we are growing. On the left-hand or right-hand side there, is a list of our board of directors. As you can see, 3 out of the 5 are actually local to Montana. One of them is our CEO, Rob Scargill. And another one, Chris Hedrick, she actually owns a business in White Sulphur Springs. So we're really focused on our people and really utilizing everybody that we have around us.
Thanks, Erin. So yeah, just touching base on jobs in the economy. We're really excited at Black Butte Copper about the jobs that obviously it'll bring at a local level, but also at a statewide level for during our construction. Here's just a breakdown of the positions we are looking to hire. during mine construction, which is expected to last 24 to 36 months, we're looking at bringing on 200 to 400 full-time jobs. During operations, which our mine life is set at 8 to 10 years currently, we'll be looking at 240 full-time positions. And the breakdown on the left, this is what we're looking at for education and experience, and just really want to touch on the fact that there really is a job for every level of experience, all the way from no mining experience to just completed high school to a bachelor's degree and upwards of that. And we are really aiming for a 40 to 50% female workforce. We do believe that there isn't a job that a female can't do at the company. And currently we do sit at over 50% workforce at Black Butte Copper. So we are building a new social outreach model formed by the Marr County Stewardship Council. And this is really just to ensure a net positive outcome for the area, not only socially, but environmentally and also economically. Some of you may be familiar with Stillwater's Good Neighbor Agreement. We did base this a lot around their Good Neighbor Agreement, but we wanted to build a model that's really fits our community and is more direct to White Sulphur Springs and their needs. So we do currently provide monthly tours, summer tours, scheduled presentations. Obviously, with the exception of COVID, we did not do our once-a-month tours that we have done in the past, but everyone is welcome, if you have a group, to call, schedule a tour, and we love to accommodate for that. We do host a transparency library on our website, which if you go onto blackbuttecopper.com, it contains all of our technical reports and all of our baseline data. And we really do try to maintain a outreach through a very active social media presence. I'm sure many of you follow us on Facebook and have seen our posts, so you're familiar with that. We try to be very active in volunteering, not only at the local level, but also at the statewide level. As Aaron said, many of us are locals, grew up in Montana, even in White Sulphur, so it's very important for us to maintain that local volunteer base. And then also with the Montana Hard Rock Mining Impact Act, which I'm sure most of the people in the room here are familiar with, but it's just a law unique to Montana where companies are required to look at all the potential socioeconomic impacts to local government and really mitigate them up front. So now into the good stuff, the Johnny Lee deposit. This is what we currently have permitted. You can see here on the slide, we'll be accessing the upper zone by a mile-long decline. This will be at a 15% grade down to the upper sulfide zone. The upper sulfide zone is solely underneath the water table, which is the dotted blue line on the screen there. The upper sulfide zone ranges from 150 feet to 600 feet below surface. It's pretty shallow dipping and has a copper grade of 2.4%. We will then drive a ramp down to the lower zone, which will be another access tunnel that sits 1,100 feet to 1,500 feet below surface. The lower zone is much higher grade. It sits at a copper grade of 6.8%. So to touch on the geology of the Johnny Lee deposit, it is a stratiform deposit of copper. It's hosted in shale-dominant sedimentary rocks. The upper sulfide zone has a copper thickness of upwards of 55 feet thick and has a copper grade of 2.6%. The lower Newland Formation, which acts as our host rock, is relatively soft shales, calcareous shales, limestones, and occasionally harder quartzites. The host rock will act as a natural buffer due to its high calcium and carbonate content. The primary structure in the area is the Volcano Valley Fault, which early development of this fault formed a shelf margin to basin transition zone along the northern edge of the Helena Embayment. And this did result in the earliest Newland deposition. The lower zone occurs with substantial bedded pyrite, and the stratigraphy is relatively flat-lying to moderately dipping. It is much higher grade. Its average thickness is 17 feet with a 6.8% copper grade, so significantly higher than the upper zone. Its host rocks are mostly silicified shales and conglomerates, and it is coarse-grained pyrite replaced by chalcopyrite. Total measured and indicated resources from our feasibility study that was completed in October of 2020 reports 8.8 million tons at 2.6% copper. We do have a deposit called the Lowry deposit, which sits 2 kilometers to the east of the Johnny Lee mine portal. We will utilize all existing infrastructure from the Johnny Lee underground. There are 5 total mineralized horizons in the Lowry deposit, which the middle sulfide zone is the highest of those. We have the upper sulfide zone and the middle sulfide zone that do merge at points for a true thickness of 220 meters of 50% sulfides. A major structure coming through the deposit, as you can see on the screen, is the Rose Fault. The Rose Fault does substantially modify the ore body and does down dip units to the east of the Rose Fault by up to 60 meters. And the lower zone sits below the Volcano Valley Fault, similar to the Johnny Lee deposit, but is not as high grade as the Johnny Lee deposit. So currently, the Lowry deposit is not permitted, and no pre-feasibility study has been completed to date. Total inferred resources calculate 8.3 million tons at 2.4% for over 310,000 tons of contained copper. Which gets into the exciting part that we're really excited about at the project is bringing the Lowry into a pre-feasibility study this year. We are underway with a 14,000 meter drill program, which is the biggest program we have had to date. And when I say underway, I say our first rig arrived on site last night. So pretty fresh, we're pretty excited about this. This plan is solely approved by the DEQ. So we'll be looking at kicking this off hopefully this week and drilling all the way up until likely mid-March. So some of our outcomes from our feasibility study that was completed in October 2020 is the Johnny Lee deposit is designed to be mined at 1.2 million tons of ore per year with an average annual production of 23,000 tons of copper metal. Our life of mine forecast production totaling 805,000 dry tons of copper concentrate, containing over 189,000 tons of copper metal. The project is forecasted to generate over 1.3 billion tons, 1.3 billion in gross sales, and 518 million in pre-tax net cash flow during mine operations. This is based on a conservative copper price of $3.20 a pound. And our construction capital costs overall is estimated at $274.7 million. So I'm sure many of you have seen our slogan, doing it right from the beginning. We really believe in this motto and have tried really hard to uphold this, which includes minimizing environmental impact, protecting all of our water resources, and meeting Montana's strong non-degradation water standards. We do have a relatively small surface footprint. We will return to full agricultural use after operations and reclamation. We really do have a location advantage. We are only 17 miles north of town, just off of Highway 89. We are off of an existing sealed road from White Sulphur Springs. We do have 2 nearby accessible railheads located at Townsend and also Livingston. We have fiber optics in place throughout the local community and also at the mine site. And we have Fergus Electric surveying a 37-mile transmission route to the mine site.
All right, so we'll touch a little bit more about our mine site now. So one of our pillars is environmental excellence. We really pride ourselves about going above and beyond. So just some key things in our plan. We are going to put in a 2-pass reverse osmosis water treatment plant to treat any water that comes in contact with any of our haul roads, any water that comes out from underground, any thing that's coming out of our process water pond, and things that are coming out of the mill. So once it goes through that reverse osmosis system, it'll go through our alluvial underground infiltration gallery, where it'll be passed through perforated pipes back into the groundwater. Another thing we're really proud of is our cemented tailings facility. I'll go a little bit more into that on the next slide, but on this picture, it's right here. It's an 80-acre facility, and it will be cemented, so essentially it'll be a dry stack facility. Some other things to point out here, our process water pond will sit right here. Our portal actually goes in right in here, and this is also something that we like to note. This is our non-contact water reservoir, otherwise known as our mitigation reservoir. So part of our water management plan is to lease water rights from upstream in Sheep Creek, which is just off the page up here. And it's actually a main tributary to the Smith River, which a lot of people have probably heard the things going on around the Smith River and how the concern affects our mine. So this mitigation pond is used just for that. So any of the water that we pull out of Sheep Creek, which we will pull out using these leased leased water rights, irrigation rights from a rancher upstream, we'll put that into the reservoir during high flow times, and during low flow, it'll be put back into Sheep Creek at the rate that we're using it for underground and for processing. So that's how we're managing our water and how we're managing any conflicts due to pulling water out of Sheep Creek and any questions that arise out of that. Another thing that we are doing, we're putting our paste or our tailings, we're mixing it with cement and we're putting it back into the ground to backfill all our stopes, so we won't have any underground openings after the project is complete. About 45% of our tailings will go back underground. The rest will go into that cemented tailings facility. And like Lacey said, 100% of the surface will return to agricultural use, so ranching use, anything like that, and no waste stockpiles will be left on the surface. So going a little bit into our cemented tailings facility, it is a world-class design facility designed to UN standards. So essentially, we're taking our tailings and we're mixing it with 0.5 to 2% binder and pumping it as a slurry into our cemented tailings facility, which will then harden, and then we can continue filling it from there. So we have 4 main fail-safes here. The first, obviously, that it's cemented. Secondly, we've designed this facility to incorporate the regional topography. So on 3 sides, it'll actually use the topography in the hills, so it'll only have 1 engineered berm on it. Again, it will be cemented, I mentioned that already. And another thing, we'll have a double HDPE liner, 100 mil thick, and in between that, it'll be a GeoNet membrane. And underneath that layer, we'll have a foundation drain. In the middle of that, we'll have a drain, and then on top of that, we'll have a basin drain system. So any water that does come in will be drained out. Something else we're really proud of, even though this is a dry stack facility, Montana passed a really stringent dam regulation in 2015 that requires all tailings impoundments to be able to withstand the maximum earthquake event and the 1.5 times the maximum precipitation event. So we've actually designed this facility, even though it's dry, to meet those standards. So in our area, that's a 1 in 10,000 year earthquake, or 22 inches of rain on top of 11 inches of wet snow. So our facility can actually hold all that water and drain it out. And once that water is drained, if there is any water, it gets pumped to the process water pond to be treated or used back into our mill or underground workings. This is a picture of our future mill site. Our portal is actually just off to the side over here. It's about a 14-acre footprint, so really small. This facility will house a traditional flotation process plant. We'll also have our paste plant on site. We'll have a concentrate load-out facility. have possibly an assay lab, and our administrative buildings and dry will be right on this site as well. So we're really proud that this is what our project will look like at the end of the mine life. If you didn't know it, you wouldn't know that this was a tailings facility, and everything else goes right back to agricultural use. So at the end of the mine life, this tailings facility here will actually be capped again by the HDPE liner, and then 6 feet of soil will be put on top of that, and then it'll be reclaimed to match the existing topography. And then again, with our mitigation reservoir here, depending on whether or not the ranchers would like to keep that and use it for stockwater use, there could be a change of use order in the plan there, but if they decide that's not what they want to do, we'll also reclaim that as well. So at this point, we'd just like to thank you all for listening to our presentation. This is actually a picture at the end of phase 1 construction. MK Whedon was kind of the head contractor for all that, but we have some contact information here too if anybody's interested in calling our office, taking a tour, or just visiting our website as well. So if anybody has any questions, we'd love to take them at this time.
Probably said this, but what's the current mine life?
The current mine life for the Johnny Lee deposit is 8 to 10 years, with Lowry coming on board, potentially adding 5 to 7 years.
I'm not sure about that. Oh yeah, the question was what drives the need for 6 feet of soil on top of the reclamation? So I'm not sure about that. We do have all of our information in that transparency library though, and it has more information on that. Yeah.
Memory serves, I think in part it was to ensure an opportunity for water to be returned to the atmosphere because you've created now an impermeable layer below it, so it won't continue to infiltrate because you've got the lining there. So I think that was the
Okay, thank you, Lisa.
All right. Thank you. All right, we'll get right into the next presentation, which is going to be another virtual presentation. The Quest for Sky Jades, Wyoming, by J.P., I apologize, Justras, is a professional mineral exploration geologist with over 30 years of experience in the mineral exploration industry. He has worked in over 15 countries on 4 continents with numerous public companies including Placer Dome, Prism Resources, Gold Star Resources, and now Jade Leader Corp. And with that, JP, can you hear me?
I can hear you. Can you hear me?
I can see you on the screen also.
Oh my God, that's terrible. I'm going to share screen and put the presentation on right away.
Great. All right. Well, thank you for joining us virtually, and go ahead and start your presentation.
Well, it's a pleasure. I apologize for doing this virtually. The border was still closed, so I'm not going to be there for the social tonight. Now, I just have to be back here.
If you have dual screens, you'll have to switch it to the other screen.
I don't, but now we should be on.
Yes, we see you. Just need to put it on slideshow.
Okay. All right, what are you seeing now?
We see your slide, but you're not on slideshow. So you go up to slideshow and go down, or down there on the right, yes, or where you're at there.
Okay.
There we go. Now we're live.
Excellent. Well, I see a couple of familiar names from last year. I gave a version of this presentation. At the time, there was a lot of background material. I'm still going to have a little bit because jade is not something that's familiar to everyone. But we're going to be a lot more detailed because we have progressed in our exploration, and we're going to like to talk about the sky jades. So we are a public company. I have to give you the disclaimer that we make projections and sometimes things don't work out. So please take everything with a grain of salt. And if you like what you see, you're welcome to look at our website, do your due diligence. Quick presentation path. I'll just tell people how I got to be doing this. I'll talk about the general market space for jade, talk about jade itself, and then the exploration side. As the introduction said, I've been working in mineral exploration for over 30 years now, lots of countries, many continents, and I really turned exclusively to jade exploration in 2017, mostly with US-based targets. Interestingly, I did not turn to jade exploration because I'm a geologist. I turned to jade exploration because besides being a geologist, I've been a jade carver for 30 years. This is kind of my path in terms of work from the late 80s when I was selling little earrings at the Student Union building in university to pay for beer, to the evolution from left to right as to the carvings I've been doing over the years. And it's those carvings that got me to be invited to go to participate in a competition in China for the first time in 2016. I had no idea what was going on, even though I'd been buying and selling jade and carving jade for 30 years. All I knew is that the price of my rough materials kept going up. But when I went to participate in this competition in China, I just started to realize why the price was going up. And we'll look at some of the numbers afterwards. But this little exhibition or competition I was at had about 90,000 visitors in 2016 over 2 days. I've gone back in 2017, 2019 to compete again. And this has really been a window into the jade world that nobody in the West really has. And part of that window was looking at, you know, first the kind of materials that they like to use. What do they really mean by quality? So these are all master carvers from China, and I did put in my little exhibition piece in the corner there. I did get a silver medal that year. And at those trade shows, they also have booths of, you know, real merchants. This is not a street market where the price is a tenth of what you should pay. These are real vendors. And looking at the prices of the rough, you know, this little slab was $115,000. This one was $2,900, a darker green. I just kind of started to get a sense that some of this jade was worth real money. And as a geologist, well, I started thinking about whether that was an opportunity. I wanted to understand why it was worth so much and how big the market was. I did sit down with another master carver and looking at different types of materials. Nice green jade from Russia. I was going $200 to $300 a pound. White jade, $5,000 to $54,000 a pound. And of course, in mineral exploration, we start with the baseline of, if we want an open pit, we're looking at $10 a ton. If we want to go underground, we need $100 a ton. So these numbers kind of blew me away, and wanted to know what the context of that was. Now, just one thing to mention quickly is I had gone on business in the mining world to China in the early 2000s, 2005 to 2007. I actually, even though I love jade, I had a hard time finding a jade shop to buy stuff at. The prices really exploded after that time. Some people will put the explosion point at about 2008. And that happened because there was a big return to market from Asian jade lovers, and also a big increase in the capacity of the industry. So in 2016, my research at the time talking to master carvers, looking up any published sources. We're looking at a nephrite jade market in China that was about $30 billion a year at the time. Number of jade carvers in major cutting centers, 250,000 to a little under 300,000 carvers of jade. And in, it was a few thousand at the turn of the century. So the huge explosion of carving capacity. Then I looked into world jade production, what we could find in terms of published data. Canada was a bigger producer at 400 tons a year. China, 40 tons a year. Russia, 100 to 500 tons a year. That went up really dramatically in 2016, 2017. These are 2015 numbers. And that's on the nephrite jade side. We'll have a little slide on that later. During that time, Burma and Myanmar went through a period of heavy mechanization of artisanal sources. They were producing about 20,000 tons a year of jadeite. Trade estimate value, anybody's guess, there's so much smuggling, $10 to $30 billion a year in production of raw material going to China. Two very important things that are happening right now is that essentially Canadian production is getting shut down due to socioeconomic and permitting issues. And Burmese production, as far as I can tell from satellite imagery, just went to zero in by November of 2020. So it's a very tight industry, a high value product at the high end, and very little production. To compare that to an industry that we're familiar with in the West, global sales of polished diamonds, 2006 to 2013, to have a good spread of data, between $13 and $22 billion a year. So the worldwide diamond industry, smaller than the jade industry in China alone. And when you look at rough diamonds, 12 to 16 billion a year. So there's a bit of a differential between the cut and the rough value, but we're still seeing that the jade industry is just much larger than the worldwide diamond industry. What changed? Why did my rough prices go up? Why so many carvers today? Why such a scramble for resources? It's really easy. In Asia, it's a 7,000-year-old market and history. It really came to a grinding halt in the late 1800s with the Boxer Revolution. Then the fall of the Qing Dynasty in 1912. So for 100 years, people in Asia weren't carving jade. Now, the demographics, 1950 to 2015, population increases, and it's only at the beginning of the year 2000 or so that wealth produced actually starts going up. So they can start to afford it again, and they come back to the market as buyers. The same is true of a number of other countries with that share Asian history. So Hong Kong, Singapore, Taiwan, same story everywhere. So, I mean, they've always wanted the jade. They would just, for 100 years, they had a bunch of problems. They had no money. The Taiwan is interesting because Wyoming did have a period of artisanal production of jade. It was really well regarded internationally. And Taiwan was one of the export markets for it in the 50s and 60s. Now, as a geologist looking at it, a mineral exploration opportunity, I went, okay, there's a huge demand that just popped up. How does that apply to the supply situation? So have enormous supply pressure, essentially have a modern market demand that meets an artisanal mining sector that's been in darkness for 100 years. So the first thing that was done is they returned to the traditional sources. The first one of those in China was in Hotian province, northwestern China. And for thousands and thousands of years, the Kudankash and Karakash rivers in Hotian was where jade harvesting happened. The engravings from the time said that it was naked young ladies would go into the rivers because their feminine attributes would attract the jade, which has masculine attributes. So that industry went into dormancy for 100 years. During that 100 years, we had the appearance of mechanized equipment. So when they went back to the rivers, the ladies lost their jobs and the heavy equipment came in. And essentially in a period of about 3 years, they just cleaned out all these historic alluvial fields. And being alluvial, once you do that, the source is gone. Then there's another traditional area that was well known in Burma and Myanmar, which was producing jadeite jade as opposed to nephrite jade, the traditional Chinese jade. But that was another place where they could go and throw a whole bunch of equipment in. So they did. This is quite horrendous, especially in a reclamation conference. But that is how much they wanted the material. Now, that mechanized extraction was about 2014 to 2020. It's another slide of that. I mean, there are no published prices for jade, but we can see how much capital was thrown at it to get to it. This is an image from a report that was just published actually in June this year from an NGO called Global Witness, and they were talking about jade and conflict. Few numbers there. Estimates of production, 2014-15, 16.3 thousand tons, and $2.2 billion to $15.9 billion worth of value. 2015-16, $4 to $43 billion of estimated value, 33,000 tons. What's happened over the last year is that all licenses that had been granted in the last 10 years have expired. There are no current mining licenses. And of course, that was followed by the coup in Burma or Myanmar. So very large political unrest. Now, these things they looked like they were operated by a large mining conglomerate, but it was really a whole bunch of small operators and small licenses. Everybody was digging their own pit. And you can see they weren't thinking too much about pit wall stability. This is an alluvial deposit. So there's consolidated gravels, but not cemented. Now imagine if you just shut down production, do no shutdown planning, no care and maintenance, and you have a monsoon. So the vast majority of these pits have now been filled with water and they're all collapsing. So as far as I'm concerned, I think this source of material has been condemned, certainly during my lifetime. It's not going to be easy to go back, even if they solve the political and licensing issues. So I did mention nephrite and jadeite. There are two specific minerals or materials referred to as jade. Nephrite is the traditional jade of China. Green, white to black. It's a tremolite actinolite series mineral. It's an amphibole group mineral. Dense, SG about 3. And again, major producers, Canada, Russia, and China. Jadeite jade is a pyroxene group mineral. It's actually the mineral jadeite. Mostly from Burma, first introduced to China at about 1784. But it was also the jade of the Mayans, the Olmecs, and the Aztecs in Mesoamerica. We don't do any jadeite exploration, so I just throw it in there to make sure people understand the difference. So, factors affecting price, having had the opportunity to go and see the works of master carvers, it gave us a great window into what they prize above all. It'll be a factor of color, translucency, size, workability, and then of course some of the aspects such as pedigree, whether it's a historical jade, and interpretation, which is the carver's skill in the stone. We looked at that to go hunting for targets because we needed to know that we were going to have the ability to access the top level of the markets. What the carvers value the most: uniform textures, solid colors, no spots, no inclusions, no foliation in the stone. And although everybody will say, well, we just want the green, the whites are fine. Some texture is fine as long as it's an alteration rind. Then we just see all sorts of masterworks that they're doing, all sorts of materials. So that got us launched into both Washington, where we have one project, 18 mineral claims, and Wyoming, 5 projects, 99 lode mineral claims. I won't talk about Washington because that's not the Sky Jades, but I will just bring up a couple of other things before we get into them. My jade exploration drivers. People are looking for geos. It'd be a good time to be a copper geo or a gold geo or any of those, but I wanted to start something different. And part of that was the process. So standard metals, minerals exploration process is information driven. Start with surface work, target identification, mapping, sampling, geophysics, move on to target definition, permitting, trenching, drilling, surface disturbance, all the things we're used to. Then modeling, engineering, feasibility, DCF revenue models, mine financing, permitting, construction, commissioning, pre-stripping, and maybe one day it'll make money. But at the end of the day, that's a decade to multi-decade end metal cycle related process. I'm at that point in my age where I'd like to see a project come to fruition, even though I already have, but I had a lot more time before. Whereas the jade exploration process is surface work, target identification, mapping, sampling, geophysics, which we've done, permitting, surface trenching, materials, production. So it's a production-driven exploration model as opposed to simply information-driven. So it took us 3.5 years in Wyoming from initiation to having materials that we were able to start marketing. So we get to that phase: product marketing, evaluation of revenue potential, and then growth and expansion on continued success. On the permitting side, I love the fact that we'll never have to deal with permitting crushers, millings, flotation areas, tailings, all of that. Even though I commend the industry of doing it much better than it's been done before. So in Washington, we do have a range of jades that we found. As I said again, it's not the focus of the Sky Jade talk, so I just like to throw them up there. One of the interesting things is we have a unique color change jade that's there. That's something that's never been identified in the literature before. This is the same piece of material. You can see that little fracture here is the same as that one. And it kind of goes from a seafoam green to a dark emerald-ish kind of green. It's a lot of fun. We're just sorting out how this actually works, because this material is very tricky. If it's not cut in the right direction, we don't get the color change and the nice colors on it. But to move on, we got dragged to Wyoming because it was active in 30s, 80s, artisanal, mostly alluvial or alluvial production, just people picking stuff at surface. But we already knew it had the kind of material that we would be looking for. This is the Craft window, North Shore Baptist Church in Chicago, 6.5 by 3.5 feet wide, done by Mr. Craft, the founder of Craft Foods and Cheese, who at the time was a fantastic jade collector. He loved it so much he had a window made out of it. And we saw these nice, tight, uniform colored carvings that were known from that period. The only thing was we had to go find the source as opposed to walk the desert and hope to be lucky and find a piece somewhere. We got involved in 2018. This is our lead project out of 5. It's the most advanced one. There had been historical workings, and the idea was just to go back there and then make sense of the geology. We found a number of different jade types. Some are a lot more exotic, but some were the kind of uniform colors that we know are appreciated at the higher ends of the market. And then some ornamental material. So this little B disc here was cut actually from that sample, from that outcrop. We've traced that one for about 600 feet, then trenched it in 2019, actually went across the structure with a nice DAT, collected a vast amount of material. It's about a little over 22 tons of samples. And in this part of the system, what we saw was mostly ornamental jades. And we're actually quite excited about the potential of that, because the USGS 2021 report on dimension, counters, countertops, ashlar inserts, still talking about a consumption with a parent value of $2.26 billion and its reliance on imports for 82% of that. We think that these stones, given their extreme toughness, the ability to cut them thin, and the ability to backlight them, have a lot of potential in entering that market, and we're working on that. But again, that's not the Sky Jades. We're getting to the Sky Jades now. The original hypothesis for the Wyoming jades was that there were gem grade jades, and there were what I've just showed, the ornamentals, or the coarser grain material. Historically, the gem grade jades, which have very, very fine texture, here's a photomicrograph of a polished surface of the gem jades, compared to an ornamental jade, where we see a lot of remnant mineralogy from the rock that's been replaced. That affects carving, that affects translucency, it affects color. So it's a little lower down the value peg. The idea was always that the gem jades were kind of part of the ornamental jades, and with weathering its surface in the desert environment, you kind of eroded all of the coarser jades and stayed with the finer jades. There was one study that was done 71, 75 at the Rhodes Pit. 400,000 pounds of material were processed, and they figured 6% was gem grade, 46% usable as an ornamental stone, 50% too coarse grain or bad competency. The gem grade was described as either veins or zone centers within larger blocks. Now, what we didn't like about that interpretation was it means you have to go through a lot of jade and hope you're lucky. What the approach we took, and this was a really important piece that we found here, about 27.6 pounds in 2019. We found it on the side of the hill where the ornamental jades were. The ornamental jades never have quartz crystals. This thing did. The grain was uniform, the color was uniform, the translucency was very high, and then we started just asking, is it a different part of the system? Right? This is in Wyoming. This is what everybody was looking for all this time. Of course, anything at surface after almost 100 years of collecting has been gone. We only found this thing because it was sticking out by about this much. And then we kind of traced it. We said, okay, let's stop looking at the ornamental zone. Let's go and look for these quartz veins, these quartz crystal bearing zones. And we found one just above where the Ventifact was found. And lo and behold, we had these slivers of nephrite jade within it was a fault zone, which is a contact between a monzonite dike or pegmatitic dike and the gneissic sequence. So we extracted a bunch of material by hand in 2020. Looks like this, doesn't look like much in the field. And we thought, what testing can we do to correlate this jade occurrence with the historical gem jades? And one of the ways that we did, because we couldn't turn back the hand of time, was decided to just take a large number of these slivers and then tumble them. Again, you'd walk by this and never pick it up. And after 10 days of tumbling in a rotary tumbler, we are seeing what people have been looking for the last 100 years after the stone has been exposed at surface and windswept. Very nice color, very good translucency, tight grain. That is what we wanted to be at. Now, in terms of taking the stone to market, how fractured is it? How uniform is it? So we decided to take some of our samples and actually cut them into a representative section of the type of jewelry that any carver or any factory might like to make out of it, but essentially de-risking the stone. So this one little piece that we had here is about 5 pounds, cut into 4 slabs. 2 of the slabs were big enough to cut what the most common piece of jewelry of jade is made out of, which is a bangle. And that's about 80 millimeters across. This one's 51 grams. It's this guy here. And then out of the bangle cores, we make the rest of the pieces, such as pendants, earrings, and ear clips and beads. So we've done our homework in terms of letting a potential buyer know what this jade can do. And that's encouraged us to take the project forward. We hope to do that this fall. The planning is that instead of 2020, where we got 50 kilos of green jade and 23 kilos of sage jade, I'll show you a picture next slide. It's done by hand drills, sledges, and wedges. We're set up now, and we've got the equipment reserved and the funding in place to go with a hydraulic hammer. We hope to get a little bit more material. So essentially do a bulk or mini bulk sample along about 50 feet of strike length of that jade bearing structure, then extract the jade from the matrix, reconcile recovered jade amounts back to total volume trenched. And, we don't end up with a % copper or grams per ton gold, but we're going to end up with a good initial starting estimate of how many kilos of what type of jade per ton. Now, the most important part, and because there's no published prices, and because jade, people ask me what jade is worth, and I say it depends. Are you buying or selling? So we have approached a number of carvers and collectors with what we had left from our sample evaluation program last year. We have started selling material. The sage jade, which is an altered green jade, which is kind of an ivory color. We've had some sales on that at 25 cents a gram, so $250 a kilo, which is, of course, $250,000 a ton. The green sky jade, the initial sale, we've sold at 50 cents a gram, and that's a piece without the bangle potential. As soon as you put the bangle back in there, the price has to go up because the bangle is the most valuable piece of jewelry you can make out of it. However, at 50 cents a gram, that's $500 a kilo, or $500,000 a ton. And the solid greens or black sky jades, we've sold a nice piece here. I've actually put it polished with some flowers in front that do the reflection. It's wonderful material. Our price on those is $1 a gram, so $1,000 a kilo or $1 million a ton. Then we know we've realized these prices. We had set those prices based on our experience as buyers and sellers of jade. And we thought these were good wholesale prices. We've met no resistance when people asked, how much do you want for that? We said, it's this much, and it was done. The only question left is, how much of this do we have, and how much will the market absorb? However, as we mentioned earlier, pretty much every other significant source of jade in the world is on its way to zero production, and we might end up being the only game in town, which might help. So the executive summary, since 2018, we've built and successfully tested proprietary geological exploration models for jade. 6 properties, all of which have jade occurrences confirmed at various stages of testing. We've demonstrated the geological potential for scale by drill. We've done in Washington and trenching in Wyoming. We're now entering a materials preparation marketing stage to generate information on potential economics. Planned mechanized bulk sample of the sky zone over an initial 50 feet of surface exposure. Hopefully this fall, if everything works well. It all works on border closures, travel restrictions, visas, and testing, negative COVID tests. And we want to increase our inventory of marketable stone for the next year, move to sales. And then also we want to identify potential clients or partners to introduce Wyoming ornamental jades to the Dimension stone market. I'm almost done. I want to leave you with a couple of reference sources. If you're interested in learning more about this, our website is jadeleader.ca or jadeleader.com. It'll take you there as well. Every time I come across an article that I think is credible, we link it to our Jade Resource Center over here. We've got some project descriptions, and we've moved, especially with the lack of travel and the lack of being able to meet people, we've moved to a lot of video material and photo galleries. Our YouTube channel has 9 videos on it. They cover anything from exploration, process, to carving the jade, to specific specimens. We've put a lot of time into this, but I think it's turning out okay. And so we have time for questions, and I ran through this. I'd like to thank everyone and happy to take any questions.
Thank you very much. Do we have any questions? I'm sure Warren does.
Thanks for another very interesting presentation, JP. I wonder if you have any comments on the Weather Channel's Jade Fever series, which seems to reduce exploration for Canadian jade to random rooting around with an excavator followed by tapping with a hammer and then cutting everything in half. You seem to have a more scientific basis than that.
Well, I have a couple of comments on that thing. The first one is that it's an abomination. It's almost like trying to reduce the gold, the real gold mining industry to placer gold miners of Siberia, right? So it has to be seen in perspective. I know those people; they have no idea what they're doing. There's been jade production in BC since the 70s, and I only know of only 2 geologists have ever worked with them. These are, they are like placer miners. They don't like people telling what to do. They want to do their own thing. And unfortunately, that show, which I refer to as the abomination, has brought the attention of both the authorities and the local indigenous communities onto an industry that was doing its own thing, but was not, because it was left unsupervised due to its size, was not doing anything in a way that a properly structured or organized or run company would ever do. I mean, you don't run these trucks across rivers. You don't do any of what they do. And that's because the show is on TV and they're always talking about the $1 million rocks. Well, a lot of people came out with, I want my piece. The regulators saw the mess they were making and said, well, we should have paid more attention, so we won't renew their permits. And it's just unfortunate that it's been done that way. But at the same time, I think that the Burmese operations were running essentially on the same principles, but at a much vaster scale. I mean, there is no, that I'm aware of, jade company that operates on the modern mining industry principles that we're trying to bring into it, or that you would see in a gold or copper or any of these other operations. So it's artisanal with big equipment. We thought we'd try to change that.
Thank you. Well, I thought I'd give you a chance to say what you really think.
Yeah.
And I can only bear to watch it if I record it and then fast forward it and watch a half-hour episode in maybe 8 minutes, tops.
I've watched 3 episodes in total. I just can't.
Any other questions? All right. Well, thank you, JP. I appreciate it. And stay safe up in Canada.
Pleasure. Thank you so much.
Our next presentation is going to be a dual presentation. Our 2 speakers today will be Dan Klein and Kirk Miller. Dan will be first here. Dan Klein brings over 20 years of mining, reclamation, and permitting experience to the Perpetua resource team. He has degrees in geology from BYU, Idaho, and mining engineering from the University of Idaho. Kirk Miller is a senior project manager for Tetra Tech. Kirk Miller is out of Helena, has over 40 years of professional experience in mine operation and reclamation, groundwater remediation, and environmental permitting. And we're going to get this started here. Perpetua Resources Incorporated Stibnite Gold Project.
Thank you. It's a pleasure to be with you today. My name is Dan Klein with Perpetua Resources. We were formerly known as Midas Gold. As of February of this year, our name was changed to Perpetua Resources. Perpetua comes from the Idaho flag, Esto Perpetua, and we are an Idaho-based company now, previously a Vancouver, BC-based company. It's a pleasure to work with Tetra Tech and Kirk Miller on the project, and I want to recognize Tetra Tech and the great work that they've done in developing our reclamation and closure plan. I'll give a little bit of background on the mining project and where we're at with permitting, and then hand the baton over to Kirk to go into a little bit more detail on the reclamation and closure plan. Of course, we're a development company, and so we have to give you the regulatory information. We're also publicly traded, and our forward-looking statements, so take a memory snapshot of that. I'm not going to read them. This is a good slide to show where we're located and some larger features of the project. So the Stibnite project is located in the historic town, or right next to the historic town of Stibnite. And stibnite is the mineral for which antimony is extracted. And as you see on the periodic table, antimony is SB for stibnite. So that's the connection there. And let's see if I can laser pointer here. Our Stibnite Gold Project is located in this area. It's about 84 miles by road from the town of McCall. And we are, approximately 90 miles from, 100 miles from Boise. There's a couple of long linear features on this slide that I'll point out to you. First of all, there's a power line that runs into the town of Yellow Pine, but that will upgrade. And that power line will run from Lake Fork down to the Cascade area and then run up into the Johnson Creek area. And then there's a small stretch of new power line. So we'll upgrade most of that. Idaho Power will do that upgrade. And of course, Perpetua will pay for it, as most things go. We'll also include a new access route, which is called the Burnt Log Route, and that's in this red color here. Some history about the facility in the area, the Stibnite mining district. Gold was discovered in 1890s, and get my numbers mixed up, and really went into action for tungsten and antimony recovery in the 1930s, 1938 through 40 with the war, the World War II, and into 1950s with the Korean War. The 1938 component that we see on screen here, mining at the Yellow Pine Pit, that stopped the passage, the volitional passage of salmon, of an anadromous fish. So in this area, the Stibnite, the Yellow Pine Pit has blocked passage from that, and that's one of our restoration objectives. In the 1960s, there was an earthen dam that failed and created a large washout. We call that Blowout Creek. It's actually the East Fork of Meadow Creek when you look at a map, and that is a large, currently the largest sediment source for the East Fork of the South Fork of the Salmon River. That's a mouthful, but it's a tributary to the Salmon River. In the 1970s to the 1990s, there was periodic mining work in the area, and that's pretty much subsided after the 1990s. And then in 2009 through 2011, Perpetua Resources, its predecessors, Midas Gold, started gathering up all the land ownership and the mineral resource claims. Left in the Stibnite mining district is quite a bit of brownfield historical mining impacts, which this map in the center shows the length. The Yellow Pine Pit here is where, as you see off to the right, is the Yellow Pine Pit Lake, and the cascading effect here of the East Fork. It's about a 26% slope in which the entire river cascades down and blocks those anadromous fish passage. We also had a lot of stream narrowing as materials were pushed in from historic waste dumps and narrowed the streams, and really curtailed a lot of the habitat that was in the area. On the lower right is where the Blowout Creek comes into the Meadow Creek and is a tributary to the East Fork. You can see the sediment in the springtime coming in. Again, it was a big blowout, produced a large land scar on the area. Similarly, we have water impacts in this area. There was tailings, mill tailings that were just discharged into the valley bottom and were later covered by spent ore from heap leaching, which is down at the lower left here. We call that soda spent ore disposal area, where heap leaching was put onto leach pads and then drawn off and put into these piles. So these are all part of the existing conditions of the site. Our Our approach, of course, is to be good stewards of the environment and also do good business as we do it. We feel like there's a win-win situation here where we can do a lot of good stewardship in restoring the environment, as well as producing gold and antimony. We want to minimize our impact, and so we have staged a lot of our operation on existing footprints. We want to leave the area better than what it is in the condition it is now. Similar to when you borrow something from somebody, you try to leave it in a better condition, bring it back to them in a better condition. And do all of this while keeping our workers safe and doing it in a safe work environment. Our environmental objectives are to remediate the water quality conditions. We talked about the tailings that have been discharged into the valley floor, along with a lot of historic overburden waste dumps and the spent ore disposal area. We want to cure that, those water quality conditions, and relocate those and get those facilities in a better settled state. We want to locate facilities on historic disturbance, as we've discussed, restore Blowout Creek, so we want to knock down all of that sediment that's coming into the drainage, and restore the fish passage that's been curtailed since 1938. Our main objective, or our main resource here, is gold at 4.8 million ounces of gold, and we also have our secondary mineral resource at 100+ million pounds of antimony. And antimony has become a new player in the markets, as it's a critical mineral listed on the U.S. critical mineral list. Not only for defense, but it's now becoming a larger player in green energy, with antimony being coming into play with new technology in batteries and energy storage, as well as solar panels, metal and steel additives for wind turbines, and so forth. The project, of course, as all these projects do, they have a big potential of bringing economic opportunity to the local economy. I won't spend a lot of time on these numbers, but of course there's a direct and indirect benefit to the communities, and we display here just a few of our local vendors that anticipate and have supported the project, anticipate a great economic opportunity. As far as the mine project in and of itself, there's several components of it that I'll display here. First of all, we have 3 open pits that have been designed. In the upper area is the Yellow Pine pit. The kind of tan color is the pit, and this is a map that is restoration, more of an end of life. So the green illustrates backfill of this pit. So the Yellow Pine pit will be mined and then later backfilled. Just to the right of that is the West End pit, and the West End pit is very elevated on the top of a ridge line. There's a portion of it that will be backfilled, called the Midnight sub-pit. As we move up valley, we get to the 3rd pit, which is called the Hanger Flats pit, and that will also be completely backfilled. One of the kind of highlights of the engineering that has gone into this project is we see a dashed line around around the west side of the Yellow Pine Pit. And in order to mine the Yellow Pine Pit, we'll divert the east fork of the south fork of the Salmon River, which currently runs right through the middle of the pit. And so in order to divert that and allow us to mine that pit, we'll create a 0.9 mile tunnel. And within that tunnel, we've designed a fish ladder to allow anadromous fish to start accessing the upper reaches of the east fork of the Salmon River, the east fork of the south fork of the Salmon River, as well as some of the Meadow Creek areas right away from the start of mining. So that tunnel will come in to play in the early construction years. The tail storage facility is shown here in the southern part of the facility. The mine is anticipated to be about a 3-year construction with 12 to 15 years of mining operations. Geosynthetic liners will be used under the tailings, and we've recently added geosynthetic to the top of the tailings to essentially make a big burrito out of it. We'll restore the channel across the Yellow Pine Pit, and Kirk will talk about that in a minute. We're looking at about 1,660 acres of disturbance. 850 of those will be on prior disturbance in the legacy areas, with 1,400 acres reclaimed. And of course, those pit walls are steep and difficult to reclaim, so those are the areas that do not get reclaimed. Our processing will have a stibnite flotation circuit and a sulfide pyrite flotation circuit. The concentrates from the stibnite flotation circuit, the antimony flotation circuit, are anticipated to go off-site for processing and refinement, where the golds will go through a pressure oxidation system and then be refined on site. Right now we're in permitting, and we are at the response to public comments. There was a draft environmental impact statement published a year ago in August, and the lead agency, the U.S. Forest Service, has been working through comments and working towards final EIS. However, they have indicated that a supplemental draft environmental impact statement will be required. So that's our next target, which we're anticipating Q2 of 2020, and final EIS with the draft record of decision in 2023. So we're well on the way, but we still have some pretty big milestones to get through. I'm now going to turn the mic over to Kirk, and he's going to give us a little bit more feedback and detail on the reclamation and closure plan.
Thank you, Dan. There have been 3 versions of the reclamation and closure plan, which you'll hear me use the acronym RCP sometimes. We produced one before the draft EIS that was used by the Forest Service in writing that document. We produced one after the draft EIS that took some of the Forest Service comments and direction they chose. And then this April, we produced the 3rd version of it because there were changes in the mine plan that structurally changed some of our numbers. So we've been through it 3 times, and we'll do it again after the draft supplemental. Or at least somebody will. I'll be retired by then. So from the beginning, Perpetua has directed us that wherever possible, they're interested in doing restoration as opposed to just reclamation. The 2 pictures here on the left is an old channel that was straight channel, vegetated, rip-wrapped, and what Perpetua is looking for is more of what's on the right channel, restoring habitat instead of just meeting minimum conditions, going that extra mile. And that's been something they've pounded into us from the beginning. The major topics in the reclamation and closure plan set our goals and objectives and strategies, how we're going to approach the project, general reclamation procedures that applied across the site, and then specific practices, which were facility by facility, what were we going to do. The reclamation schedule, which is important because you had lots of moving parts on this project. How could you do concurrent reclamation and when? And we produced a couple important appendices. We produced 29 end-of-year maps for the 42-year life of the project. And this helped us, and the agencies really asked for it, to see that sequence of what's happening on the ground. And then we did a root zone suitability analysis for development rock, looking at, we've got growth media on top of development rock. You know, what is the impact of that development rock on rooting plants? Interesting thing on this document, in my kind of history of doing permitting, this is a very detailed document. We look in great detail at the acres, volumes, and timing of reclamation. So our general reclamation procedures, you know, was decommissioning, contouring, grading, growth media management, and mass balance. How much soil do we have to salvage? How much soil growth media do we have to put back? Any plant nutrient deficiencies we need to try to account for. Seeding, planting, reclamation monitoring protocols, you know, establishing now what is the frequency and type of monitoring we're going to do, and then reclamation performance standards. What are the targets we're going to try to hit? If we don't hit them, what are we going to do? Soil salvage, key part of any reclamation project. Did detailed soil mapping. We set criteria for salvageable soils. It was tied to slope. It was tied to how many coarse fraction and other chemical properties. We did volume calculations by soil map unit and by facility, so that we could look at a facility and say, when we disturb this, how much soil we're going to salvage, as well as making decisions about a soil map unit and how much of it is salvageable. And we've adjusted those numbers through the 3 versions of the document. Then we evaluated methods to supplement quality and quantity. We investigated composting. It's a remote location, not a lot of source material, and so that's growth. Compost is going to supplement quality, not really be a quantity supplement. We've looked at and identified a glacial till on site that's free of the mineralization you find in a ore body that we're going to use to supplement some shortfalls in salvage soil. So for each facility, and I realize it's too small to read, but for each facility on the site, we developed a soil profile. It said based on the underlying materials and slope, whether they're cover liners, proximity to floodplain, we developed a different profile. In general, the orange is seed bank material, which is wetland floodplain areas. The green is growth media. The kind of light yellow is development rock. The brighter yellow is where we have liners. So for each facility type, we had to go through and look at that package, and then that was used to calculate volumes, because every facility has a different profile. So then getting into, this is really mislabeled, site disturbance and reclamation volumes and schedule. We generated a couple of big spreadsheets that looked at subparts of every facility and its sequence of time and how much soil was coming off, how much soil was going back, how many acres. We have these spreadsheets with 1,200 columns, 30 rows. So for every facility, we can look at how many acres disturbed in what year. And we can look at what are the total disturbance for every year, what's the total disturbance by facility. And that allowed us to do a couple things. One is, what is our mass balance of salvageable soil? And then what's our sequence and timing of when that soil is taken off, needs to be stored somewhere, and then when does it come back onto the facility? And then we did a second table similar to this that did the same thing with volumes. So we could look at, that was useful for timing of costs of when you're going to have to be moving soil. We produce that graphically as well. So for every facility there, we have a tag here showing the year in which you're going to disturb that, that specific piece of real estate. And then did the same thing for reclamation. There are a lot more tags here because some facilities, like if you look down, oh, here I did. Yeah. So if you look down here at the tailings storage facility, because it consolidates and settles over time, we have different sequences of different years we can go in and place cover back on the tailings storage facility. This was important input for reclamation costing for the feasibility study and will be when we do bonding calculations of what years are we moving, what kind of volume of material, what years are we having to buy reclamation seeds, stock, et cetera. So it's a valuable document for those cost estimates. Develop planting prescriptions based on different microclimates, cool aspect, general aspect, mesic, and we also had a temporary cover planting prescription. So it identified what are the seed mixes, what are the plant stock. This is an area, it's a combination of trees and grasses, so we've got both planting stock and seed mixes. This is one of the north end of the maps. You can see the different colors for the different prescriptions of soil, and there's a map for three maps to cover the whole site. One of the appendices is end of year maps. As I said, we produced 29 of them. 42-year life for the project. Even though we mine 12 to 15 years, have to wait for tailings to consolidate before we can cover. The groundwater modelers have projected that we have water treatment going to year 41 after we close the tailings impoundment. And so we have to maintain a little footprint for water treatment plant. So I'll just kind of run through some of the sequence. Year 4, a lot of active mining going on. One pit is backfilled, one active, one starting. Tailings is almost to full size. We don't have full disturbance yet. And there are several areas on here that are crosshatched where we have completed reclamation. So we're tracking those acres as well. Mining year 15, mining's completed. Reclamation is well underway, but the tailings storage facility is consolidating. So it sits from there to year 24. And at year 24, we're able to come in and bring cover and put tailings or put growth media on the tailings storage facility. And you can see we're restoring Meadow Creek across the top of the tailings. So there's a whole nother paper to be given. Maybe that'll be next year with the guys who designed all the stream channels. So there's stream channels going across the tailings facility, across the Hanger Flats pit, and across the Yellow Pine pit, restoring stream habitat. So that's been a big challenge. Usually you want to keep water off tailings facilities, right? We probably all design lots of diversions to do that. But in this case, recreate the wetland habitat because the tailings storage facility takes out a lot of wetlands. This was a way to restore it in kind in the same drainage. So one of the key issues here has been Yellow Pine Pit, as Dan talked about how it looks currently. Blocked fish passage since '38. The new Yellow Pine Pit will occupy this same area. So the river's diverted, Yellow Pine Pit goes down by 400, 500 feet. Yeah, and then backfilled, you have a few high walls left that will still be exposed, but you backfill and you recreate East Fork, South Fork, Salmon River. Across that surface, reestablish fish passage and create a lot of habitat. Stibnite Lake down here is a temperature moderation facility that was added recently because of temperatures in East Fork were predicted to be potential issue. So major feature here, and part of the whole restoration model of the site. One of the other things we looked at was we got development rock underneath a foot of growth media. We're going to have roots into development rock. Our soils in some areas have naturally high metals in the soils. So to investigate how much of an issue that was, we went and Stibnite Gold had 4,800 soil sample results. They're shown on all these little black lines. They'd collected all these to do exploration. So we took that data and crunched those numbers and identified that we have two distinct populations out there. A mineralized area, which is generally east of this line here, non-mineralized on the west side. So we have two soil populations with very different metals concentrations. And then we did aerial photographs and did some ground truthing, mapping vegetation at those sample locations. And this is sample locations for undisturbed ground. If there was sample on a disturbed soil, we did not include it in our analysis. And so we looked at vegetation across those two areas, and what we found was there was healthy natural vegetation across both populations, that there was not a significant difference in plant species richness or lodgepole pine tree height, whether it was on high metals soil, which were well above typical phytotoxicity levels published through any number of publications, and those in the background. So these plants and trees had adapted to those metals concentrations and were thriving. So based on that, we're looking at collecting seeds off the mineralized areas, using those as part of our reclamation seed mix, and any way we can collect seeds off shrubs and others for our plant stock, so that when those plants send their roots down into the development rock, we have, they're going to be successful, is the kind of model we're working under now. And this is based on some initial investigation using soil exploration data. We haven't done trial plots, but the initial look is that we're not going to have problems with that development rock or with our soils with high metals limiting our vegetative growth. That was a table in case somebody asked a specific question. So, any questions?
Yes.
What is the supplemental EIS going to be on?
Let me take that one.
I was going to say, good question.
So the question was, when is the supplemental EIS?
Oh, what's it going to be on?
What is it? What is it going to address?
Okay, the supplemental EIS, from what we understand, it's going to narrow down the alternatives. They had 4 alternatives in the draft EIS last August that included a different location for the tailed storage facility, a different access route, and a more simplified mine plan. And our understanding is they're going to take and eliminate 2 of those alternatives and narrow it down to a main alternative of our modified mine plan and a second alternative of a different access route. I'm not sure if that answered your question or not, but that's what it's addressing. So the draft EIS last August it was deemed maybe a little bit insufficient. And so they wanted to do a supplemental to cover some bases that didn't get covered in that August draft. Good question. Other questions?
In the past, the state of Idaho has taken a pretty minimal approach to reclamation bonding amounts, at least by Montana standards. So having the Forest Service as a partner will, I think, change that. But is it premature to talk about a bond amount for the project?
Amount, yes. As a dutiful company internally, we're estimating those amounts. But the state of Idaho just went through a new rule-making process in which they worked with the Idaho Mining Association and other stakeholders to really bolster those rules around financial assurance. And so we've really stepped that up. We're using standardized models like Nevada's CERC model now. And in this project, we have about 5 different stakeholders between the State Department of Lands, the Forest Service, Idaho Department of Environmental Quality, State Department of Water Resources, and the Army Corps of Engineers all have fingers in this financial assurance pie. And so right now, what we're trying to do is outline the process and not really start talking numbers until we have a federal action identified in the record of decision. And then we'll have the process. Our desire is to have the process and the framework in place so that we can put those numbers to that framework. Large numbers is what we're seeing.
And I think also, it was an additional addition that they're now bonding for the maximum cost. I think Grouse Creek was an example where project stopped before it was finished, and so the closure costs were much higher than they would have been at the end of the project. So I think there's some of that being rolled into their costing too.
Zortman?
Yeah, but I think Idaho's example was
So one of the new rules that Idaho has is that you have to bond for your reclamation plan. And our reclamation plan includes restoration of almost 6,000 feet of stream. So that's a big cost. I mean, it's not just, as we saw on the slides, an armored ditch. It's habitat stream that we're restoring. So we're anticipating bonding for that large value stream restoration, as well as backfilling the Yellow Pine pit. So if the company loses ground and the agencies have to call in the bond is estimated for rehandling 7 million yards of backfill in order to backfill the pit and restore the East Fork of the South Fork of the Salmon River across the stream, across the pit, because that's what our plan says we're going to do.
Project. Thanks for sharing that with us. I was curious, like you said, we usually divert streams and waterways and that sort of thing around TSS. Can you tell us a little bit about some of the cautions or design elements that are going to kind of go into routing and through the TSS?
You want to do that or you want to do it?
I'll take a whack at it, and Kurt can fill in the blanks. First of all, during operations, we divert Meadow Creek, which is the creek that comes across the tailed storage facility. We divert that around the facility. So during operations, we're keeping the clean water clean by diverting it and getting it back in its channel downstream. And then when we restore the stream across the backfill, across the tails, we've designed it. I didn't do it, actually. We had a consulting firm design it for us, such that it's about a 100 to 200 foot wide corridor that will be lined. So there's lining on it, and then about 10 feet of material on top of that liner which will allow the stream to have some hyperreach influence in that 10-foot zone, and keep it from being exposed to the tailings underlying as well. And the 100 to 200 foot wide corridor will allow the stream to naturally evolve along its course over time. So those are just some glimpses into it. Any adds there, Kirk?
I guess the other is, and there are berms built, lined up on each side to keep it from going outside of that line channel onto the top of the tailings. So it's restrained, but it still has room to meander within those 200-foot width channels.
Are they gonna build a mill at this site, or ship the concentrate, or what are they doing?
Yeah, we do have a mill built into it. I didn't point that out very well.
It is right in there.
So that, our processing circuit that I showed will be in that mill footprint. Concentrates for antimony are anticipated to be shipped off-site, but gold processing is anticipated to go to all the way to doré stages.
From online, how did you determine how far fish will swim up the fish tunnel with ladders? And is darkness a problem?
Every component is a great question. There are fish ladders in tunnels that we've identified, but not this length. Every component of the fish tunnel has been proven, but this is the first time we've put those together in a fish tunnel of this length. So just to give you a snapshot, the fish ladder is looking at 22-foot long pools with minor 1 foot or so jump stations. I don't know what you call those. And we are anticipating lighting the tunnel. The question about lighting is a question that we can't answer, but we do need to get into the tunnel for maintenance during low water times. And so we're anticipating lighting the tunnel and providing some ventilation, of course, for access and maintenance.
And I think an important thing, because that question's come up before, is that the fish aren't going any farther than the old pit pond now. So if they don't use the tunnel, it's no different than current condition. And when the tunnel comes down and the pit restored, then they have good flow. So even if they don't, it's no change from baseline.
We have, as an adaptive management component of that, we have built in, if fish don't use the tunnel, then we've built in a trap and haul them up method to allow them to access there. I'm pretty confident they will. We had in 2019, there was an avalanche. There's about 4 avalanches that covered the road, and those avalanches brought down a huge pile of lumber with them, Lincoln logs all stacked together. The fish made it through that, and we had Chinook salmon upstream from that the following August. So if they can make it through that, I'm certain they can make it through a fish tunnel that has been engineered and designed for that purpose. And that. 0.9 miles, just under a mile.
What are your anticipated markets for the antimony concentrate, and are they all in the U.S. or elsewhere?
We've a lot of anticipated markets. Antimony is, of course, a strategic mineral. There's a lot of uses from fire retardants to metal alloys, and more recently, the battery market has really sprung up. We're anticipating right now mostly U.S. markets for that antimony.
Yeah, I don't think the Department of Defense would like us send an antimony to Russia, probably, since it's a strategic defense metal. Beer 30?
All right, thank you. All right. Well, I appreciate all of you surviving some of the virtual obstacles we had today, but thank you, and thank you for all the speakers that were here, as well as virtually. I think today was a very productive and informative session, but now it's time to drink beer, and well, close to. It starts at 5 o'clock, same location as last night's social, so thank you very much, Pioneer, for tonight's social. And tomorrow, the session starts at 8:30, not 9. So remember that about 10 o'clock tonight when you're trying to make that decision. But also remember that you have evaluation forms in your book. Please fill them out so that Susie and the team that puts this conference together can get your input into next year's conference. And again, professional development hours, if you're looking for them, there's a form out at the desk, fill it out, so Susie will get you your professional development hours. And again, thanks to all the sponsors, and make sure you stop at all their booths. And with that, Susie, did you have something? Okay. Warren?
And thanks to you, Kevin, for an impressive maiden voyage as a day chair.
Well, I'd like to think this is going to be my one and only voyage, but I did appreciate Susie asking me less than 24 hours ago to do this. So, but no, I'm happy to do it, and I guess it's the evolution. I'm the 3.0 or 2.9 right now. So everyone have a great evening. Enjoy the social tonight, and we'll see you in the morning.